started, but unfortunately, it was a little bit complicated to make it happen. So eventually, we'll do that after the conference. Okay. So this is it for me. Did you want to add anything, Stefan, or?
So we start with a session of paper, 3 paper, and Pierre is supposed to start.
Started, but unfortunately, it was a little bit complicated to make it happen. So eventually, we'll do that.
Maybe you have to wait a bit.
So
Okay, okay.
Maybe we can, Pierre is supposed to start at in 10 minutes, but you can maybe. Paper, 3 paper, and Pierre is supposed to start.
So yeah, maybe we can wait for 10 minutes,
Yes.
just so that people who are watching us online follow
Maybe
the
you have to
schedule
wait
in
a
a
bit.
reasonable
Yeah.
way. So if you want
Maybe we can, Pierre is supposed to start at in 10 minutes.
My name is Pierre Lecomte. I'm an associate professor at École Centrale de Lyon in France. And today I'm going to talk about you from a work we did with José Miguel Fernandez, a composer from IRCAM, for spatial granular synthesis with Ambitools and Supercollider. There is another paper on granular synthesis tomorrow, so I'm eager to see that too. So granular synthesis is based on pioneer work of Xenakis and Gabor, notably. So the idea here is to take some sample of sound and break them in very small, short segments called grains, and repeat many grains to form some rich textures and complex sound patterns. By playing on the length of those samples, the speed you play with forward, reverse, and the envelope you apply on them. So from the pioneer work, then came a natural evolution of this concept to spatial granular synthesis, to put each of these grains in space to form some swarm of sound, and to play with this swarm all around you, let's say. Today, we're gonna talk about spatial granular synthesis with higher order ambisonics, and I'm going to present you the code we've made in Faust to produce some grain swarm and the different parameters. So this, thanks to Faust, this was compiled for Supercollider, and the wrapper is there, let's say. So José Miguel did this work in Supercollider to play with the granulator, we call this tool. And then he developed as well a 3D visualizer to see the swarm and interact with it. So the idea here is to produce in the DSP n parallel stream of sound grain. So and each grain of each stream is positioned in space with spatial coordinate, radius, azimuth, and elevation. And here you can see on this slide the graphic user interface of the granulator if I was to compile it with Faust2Jack, so generic user interface, and to see the different parameters. So you have azimuth, elevation, so you will give some range where the grain will evolve. The same with radius. So this will define a spherical shell sector. And we have some envelope. We can select between input or sound file that will be embedded in the code. The record button to take the input buffer. Gain, we can play with the length of each grain within the range. The speed at which we read the grain, which can be forward or reverse. Given here by these indicators. We can crossfade between two envelopes, and the shift min and shift max is the position in the buffer when you want to read the grains. So more in depth, how does it work? So if I consider just one stream of grain, so it's continuous signals, and it's made of concatenated samples. So I play a grain, then I play another one, and etc. And to do that, I have to produce a read index signals, which gives over time which samples to read in the sound file, in the buffer. And to produce this thing, I will use some counter, which starts, let's say, at sample 1000 and 1001 and so on. And when I reach the maximum of the grain duration, I reinitiate the counter. So the read index signals will have 4 parameters, which are the duration of the grain, the reading speed, the starting index, and the reading direction. So here in this graph, you can see in blue some read index signals. So the first one starts at 0, start of the sound file, and when it reaches maximum, I have a new read index. These ones go in the reverse direction, and so on. So I have this triangular shaped reading index signals. And here you can see, for instance, the starting index. So I start the first grain at 0 at the start of the buffer. The second one, we start at something like 42, and so on. The duration of the grain, and the read speed. The read speed here can be between 0 and 10. Like if it's -1, it will slow down. And if it's above 1, it will accelerate. So to produce those kind of signal in Faust, at the core of the code, I will use some random signals, so NO, not air noise. And I need, for each parameter of each grain, each stream, sorry, I need a new noise, so decorrelated noise signals, decorrelated values. So we are using air noises and not noises, because we need different seeds for the noise generator to produce true decorrelated signals. And those noise values are sampled and old during the grain duration. So that's like rolling a dice, and I have the parameter of the grain, then the counter starts, and when it reaches the grain duration, I sample new values for each parameters. So to trigger those, so it's this sample and hold function. So I have here, you see a noise, then it's scaled and shifted with this value between Lmax and Lmin here. And the select to primitive helps to select either the noise or it's the sample at the time, and it's triggered with trig functions, which is always 0, and then suddenly it's 1 only when the grain reaches its duration value. That's the idea. So we have a way to have random parameters within range for each grain, each grains, and some extra control parameters. So Jose Miguel asked me to add some features to the granulator. So he wanted to add some grain envelopes. So he gave me here a bank of 10 envelopes, and you can choose at runtime a crossfade between two of any two of this set. As well, we have a grain probability slider, which will play or not the grain depending on the probability value. So that helps to have to play with the density of grains in the swarm. And a nice feature he wanted to add as a composer, he's selecting which sound samples he wants to work with for its grains, and he marked in some samples where the grain should start. Here, for instance, you see with the red bar. So in the codes, you can give this sample index as a waveform, and when you compile it, either you take true random value within the buffer, or you can take random value among these markers. So you're sure that you have the nice grains all the time. Because sometimes if the random value goes in silent region, the grain is kind of useless here. All right. Then I produce a stream of grain. Then I produce n stream of grains. And each of these streams is specialized on the spherical shell, as I mentioned to you before. So for the coordinates, it's randomly chosen within range in azimuth, elevation, and radius. So again, it will give you a spherical sector. So we add the radius as well, so the grain can be closer or farther. So we play with the volume here, the roundness of the grain. And each grain is then encoded in H higher order ambisonics format with the encoder provided in Ambitools. So at the end, we have we have L signals, L plus 1 square signals, so HOA buffer. So each stream is are summed, if you want, before are encoded, and the resulting encoded sound field are all summed together to produce the HOA buffer signals. We have an option as well to send the values of the coordinates as well with the amplitude of the signals of the grain itself to drive the 3D visualizer with OSC values. So to do that, we were using some bar graphs in Faust, bar graph primitives, which give us the values. And those bar graphs were during the compilation with Faust to Supercollider with OSC flag. Then we can retrieve those values, which are sent to the 3D emitters, which then produce this kind of view here. Faust compilation issue, let's say, or because this approach is quite brute force. Why? Because we need for all the features Jose Miguel asked me at the end, we have 8 decorrelated random noise signals for each of the n stream of grains. So that's a lot, let's say. Then we have at the output L plus 1 square HOI signals. And at runtime, we want to select between 2 envelope signals. So I will have 20 envelopes to compute at runtime. And we have as well a selector between live input or sound file embedded in the code. So at the end, I have 28 times n plus L plus 1 square signals at audio rate for this plugin. And when I increase the number of stream as well as the order of the HOA signals that I want, the Faust compiler doesn't like that very much. And we've made some tests of the time spent with Faust time granulator, the DSP, by fixing either we fix the HOA order to L equal 3. So it will give us 16 signals at output. And we increase the number of grain stream in parallel. So that's the blue and orange curve here. And if we fix the number of stream, let's say 4 stream of grains, and we increase the HOA order. And you see that the Faust compiler at the evaluation step and propagation step start to increase like drastically. And then I stopped here at L equal something like 10 or N equal something like around just 9 here, 9, sorry. And you see that that's still an issue. So sometimes it finished to compile, but in the current states, we advise the user, so Jose Miguel is doing like that, to keep N low, like let's say 1 or 2 stream of grains, increase the HOA order you need, and then run several instances in your output software, let's say Supercollider. And here it's really important to have this air noises primitive in the code to ensure that each instance have different seed for each stream of grains to avoid having the same swarms. Even if you play with the range, you may have some correlation between each stream of grains. Okay, so now the Antes Collider part. So Jose Miguel wrote a library which is called Antes Collider, which is at the cross between Antes Cofo and Supercollider. So that's the tools he's using to do his musics. And the idea here is like we simply use the Granulator DSP and Faust to Supercollider tweaked by Stefan here to produce a nice UGen. Then he include this in his library. And OSC signals are used to communicate with Antes Cofo and Open Frameworks, which is the software we use to develop the 3D visualizer. The 3D visualization itself is made in Open Frameworks, and so as I mentioned before, we use OSC signals to visualize the grains. So those are the red dots. If you notice the size of those dots are depending on the amplitude of the signal itself, which means that when the probability kills the grain, it will disappear on the view meter. And the purple cloud here is another layer, an ambisonic energy visualizer. So to produce that, we evaluate the square amplitude of the HOS signals, and then decode that on a very dense virtual loudspeaker array to help us to see where the sound energy is. And we used around 1,000 nodes sampling grid, and we use the sampling decoder here, and that's driven as well with OSC. So that's another layer to see this purple cloud here. Okay, so to conclude this paper, so we've made this spatial granular synthesis tool that we call the granulator. So it's available as open source code in Ambitools. And this work was made during this spring in Gram during a residency of José Miguel. So I was in French we say rime. I was doing the development he asked me, and he was asking more and more features, but we had fun with that. And so we still having some issue with high order, ambisonic order, or very high number of stream of grains. So maybe we could improve this code by using some the future or maybe current end-demand primitive to kill some signals at runtime. And so José Miguel has this tool now, and he will use it. I think he's using it right now to produce a live electronic music piece called Gnomon, which will be premiered in June 2025 during a GMLAC conference. So I invite you to come and listen to what he did. So thank you for your attention, first of all. And in the remaining time, I asked José Miguel to do a video of what he's doing, because I think it's pretty nice to show you that. So I will switch and try to go back. Let's try. Okay. So you see here he has in his view meter, he has all the parameters. Behind the scene there is an Antes collider, and he's playing with the range of azimuth min, azimuth max, and so that can produce this. So I think it's a drum samples here, and we can see the swarm of grains. So here is extending the range where the grain can play. He's increasing the probability right now, so the density of grains will increase as well. Reducing the duration of the grain. Changing the envelope. Again, increasing the length of the grain, and so on. Maybe I go a bit further in the video. Obviously, we're just hearing the one signals of the HOA signals, just to have an idea. But with a loudspeaker array, it's more like you will see. So it's playing with the speed reading, so the sound is played. Selecting the different sound samples with this slider here, and so on. Okay. So that's the Collider part, and I'm gonna try just to show you. So with the Faust 2 jack. So that's the one here live. I'm playing live, so I can select the sound file as well. The duration of the grain. So 2 seconds here between very short and very long grains. So if I go the read speed between, okay, so now it's. Can I forward reverse? So if I go between, so now I just play reverse because both range are in the negative part. Shift min, shift max, so I can go with more at the start of the sound. If I do. Very short grades here. And depending on which one. But I'm not a composer, so I don't know if it's nice sounding, but yeah, that's the tool mainly. Okay, so thank you for your attention, and if you have any questions, I'm happy to answer. Je sais pas qui donne la parole ici.
Thank you very much, Pierre, for this presentation. We are very happy to be able to get the inside of this project, and because we invited in Paris 8 José Miguel Fernandez to come and give a seminar, 2 seminars.
Okay.
And he presented the artistic part of the project. It was at the beginning of this year. And I have 2 questions, very small one. When you don't use a buffer or pre-recorded sound, do you have a delay line for the direct input signal, or as input, or is it? How do you manage the?
So for this part, we use the read and write table, if I recall. So we have fixed duration, so you have to give the size of this buffer at compilation time. So I think we take something like 1 or 2 seconds.
Okay.
And then we have the record button, which fills circularly this buffer.
Okay.
We've read that we may have some clicks at sometimes when you read while it's written, but we solved this problem with envelopes so far, and I've seen a paper like dealing with how to deal with this problem that I didn't code that because with the test we did with José Miguel, it was working, so okay, I stopped there. But yeah, like we're not using a delay line to solve this issue so far.
Yeah. Second question is about the spatial rendering in 3D. In fact, as you randomize everything concerning the position of the grain and even its existence in real time, don't you get sometimes kind of holes and homogeneity in the rendering, having, for instance, a lot of grains on the right, for instance, and kind of holes perceptive holes in the 3D rendering?
I haven't experienced in 3D much, like just during the residency. So with preliminary test, it was working for him again. And so the noise we're using are, I don't know if air noises are Gaussian or uniform distribution, but that's the key here. They sample your range. I don't remember which distribution it is, but we didn't see much happening. And the probability slider is the grain is computed, and it's just like gain is 0 or 1 depending on the probability. So I compare the probability slider with it's a comparison, and if it's below a certain value, it's 0 or 1, and that will kill the sound even if it's computed. And because the amplitude is 0, it will disappear on the visualizer. So that's how it's done. So it's quite simple, but it's working. Yeah.
Thank you very much.
You're welcome.
I have a slightly harder question, or tougher question, maybe. Like that's so. I was wondering, because I know that Jose Miguel works a lot with the kind of things that you presented. So, so you talked about the computational limitations of the compiler, the time it takes to produce something or whatever. Did Jose Miguel say anything about this? You know, like meaning that did he try, for example, to do this with another platform, like in another environment, and like, how does his other implementation compare to the one that he was hoping to get here? And I'm sorry to ask this question and being the devil's advocate, but I'm just curious, you know, because
Jose Miguel is I don't know, he's a brute force guy. So he has a very powerful Mac, and he's okay to wait 15 days for the compilation to. So he was doing like that, and his request were like, I want 1,000 grain at order 10. Give it to me. So and yes, you can put that compilation in the code, but then the Faust compiler take ages, and then that's Stefan who could better answer, I guess.
But then, like, did he try to do the same thing in other environments? Like, is it something that he mentioned, or like?
I mean, I was doing it on Linux with my laptop, and he was doing it on Mac for Faust Supercollider. I was doing for Faust Jack, and it was the same.
I don't think he said nothing about that.
Yeah.
He said nothing about trying to do granulation and ambisonic stuff outside of the Faust context. So I don't have any comparison point. Actually.
But maybe you could, I don't know, for the first compiler, like because he wants to flat everything before, and because the number of signals like explodes. So maybe it's. We were observing like the RAM usage and the CPU for the first compiler. It was like increasing a lot. That's amazing.
If you want to do, we know that during the evolution of the fast compiler, so obviously Jan can better answer than me. We at some point we were able to solve explosion in compilation time by doing kind of memorization at different places in the compiler. So maybe there is still something not done correctly at some point, but it's not easy to find out, or it's an algorithm by itself that has some polynomial, or I don't know, kind of explosion, and in this case you can't do anything. But we don't know exactly.
I think as a composer, he enjoys as a composer, Jose Miguel enjoys the quality of rendering of Faust. So I think he puts the emphasis on Faust. He could use I don't know, Max directly, but he told us he prefers the rendering of Faust.
So that's very good.
Just a quick comment about the holes in the distribution. this is my experience when dealing with reasonable ambisonic orders. The resolution is still too, well, it's kind of good, but I'd say my experience is the resolution is too broad to perceive big holes in the soundscape, especially for granularized sounds. Maybe also a quick question about the spatialization. So I've seen you have sliders basically to set, I think, elevation and azimuth angles where the grains can occur, or basically a range, a geometrical range where the grains are distributed.
It's a geometrical range.
Is it, maybe that's just an idea for a feature. Are they uniformly distributed in that area, or is there some kind of, well, let's say more center-focused probability?
That's the air noises signals, and I don't remember if it's uniform or Gaussian. I have to check the doc, but that's the answer. We are using air noises. And we observed that because first I was trying to reduce the computation, and I was to use the same generators for several parameters. Let's say one noise signals will drive, I don't know, the grain duration and the radius, but it's correlated, and you can observe some weird stuff. And especially if you use the same noises for the different coordinates, you will just play on the line, and or the coordinates are correlated. So it's really important to have decorrelated noises to randomize everything. And that's why we use the foreign function not given by Faust, air noises.
Thanks.
Last question, thanks. It was really amazing. You were talking about the compilation time, but what about once the sound is compiled, how heavy it is for the CPU?
The CPU usage during runtime, you mean?
Yeah, at runtime. It is very heavy, or it's...
No, it's quite low. Yeah,
it's quite
low. Even on mine and on his,
and
even
then
lower.
You can have other things running.
So he's at the end. I think to produce the video, he compiled like with n equal 3, 4, something like that, and then runs like 10 instances of the in the on-test collider, and that it drives like that. Yeah.
Okay, thank you very much.
And again, it's really important that the noises are decorrelated when you run, because otherwise it's the same trajectory in the, Okay. Okay.
Yeah. Next paper is differentiable DSP in Faust. Sorry. Thomas Rushton, who is a PhD in the MEVO team with us in Lyon, is going to speak about his work on differentiable DSP in Faust.
There we go. Wonderful. Can you take the meeting? All right. Let's think about it. Is that okay? Hi. Okay, cool. All right. Good morning, everybody, and thank you for having me here today. Stefan sort of already introduced me, but to recap, I'm Thomas Rushton. I'm a PhD candidate at INSA, that's the engineering school in Lyon. I'm also a member of the MEVO research team, which is a team within the broader French research organization in RIA, and within our team, that's where the sort of core developments on the Faust programming language occur. And I'm going to talk about differentiable programming and some differentiable DSP in the Faust language. So let's go over quickly what I'm going to talk about. So some fundamentals on differentiation. Hopefully that's not going to be too dull and too, well, it's going to be quite a lot of notation, I warn you now, but it's all like high school level stuff, so don't worry. Some dual number arithmetic, which I'll explain. Automatic differentiation. And then that's going to lead us on to the ability to write differentiable code in Faust, and then I'll hopefully be able to demonstrate some parameter optimization problems using automatic differentiation in the Faust language. Okay, so let's talk about differentiation. This equation may be somewhat familiar to some of us in the room from secondary school or university looking at calculus. Fundamental definition of the derivative. It says if we take 2 points on a function f, separated by some value h, we get an estimate for the derivative of the function at that point, at the point x. And that looks something like this. So depending on the value of h, so x and x plus h, the functions of those values are going to give us, joined with a line, a secant line through our function. And we get, with this value for h, quite a poor estimate for the derivative. But if we reduce h, things start to get a bit more respectable. Those of us who remember doing this one at school will know that the derivative of f of x equals x squared should be 2x. And if we reduce h even further, let's take it down sort of to its logical conclusion. We now see we get a pretty good estimate for what the derivative of this function should be. And we get a nice, we've gone from a secant line to what looks more like a tangent line, a line that sort of hugs the edge of our original function like so. Right, now let's have a small but non-zero amount of fun with the infinitesimal part. That was h of the equation we just looked at. So let's let h equal this product of two interesting looking symbols. So x dot, we're going to use Newton's notation for the derivative. And this is just to avoid a little bit of notational ambiguity with the prime notation. And then we've got this epsilon, which is what's termed a nilpotent symbol. And it's a little bit like the imaginary unit in the complex numbers, but this one has a different set of properties. It's non-zero, but it's square, and any other, its cube, its fourth power, etc., are all equal to 0. Oops, I missed a slide there. So we can substitute that into the equation we had and then rearrange, and we get this interesting looking guy here. Now, if we say that f of x is equal to x, we get this interesting looking expression here. And this, the colored item to the right, my colors maybe are not quite so clear on the screen up here, but the x is blue and the epsilon x dot is green, and this is a dual number. So the blue part represents the primal expression for f of x, and then the green part is its tangent. And one way of thinking of this is as a truncated Taylor series expansion. And we've got these cancelling terms here. These disappear because epsilon squared, as we just saw, is equal to 0. And so we're left just with the first two terms. We've got the primal, which is x, and then we've got its derivative. And the f prime is 1, so that vanishes. And so we're left with the x plus epsilon x dot. Now, why would we want to do this? Well, it turns out there are some interesting properties that emerge from passing around dual numbers. So we can apply our standard arithmetic operations to dual numbers, and we get some interesting results. So take the product rule, for example. If we take the product of two dual numbers and just expand the two terms as we would if we were just multiplying out a polynomial, we get UV, which is the primal for a multiplication, and then we also get grouped by the term, grouped by the symbol epsilon, we get the product rule of differentiation, that U times V dot plus V times U dot. There is also another term, but that has an epsilon squared in it, and that's equal to 0, so that disappears. We get something similar happening for the quotient rule, except that involves an extra step, which involves taking the reciprocal of a dual number, which is the, do you see my mouse? Yeah, this nice looking chap here. Okay, anyway. But we get the quotient rule, which, if we've ever studied sort of rules of differentiation, looks just like this. And this is all just by carrying out fundamental arithmetic operations. Okay, using the Taylor series expansion, we also get some nice results for trigonometric functions. What have we got here? Natural logarithm, exponential, and power rule as well. And if V here was a constant, a numerical constant, then V dot would equal 0, and this slightly ugly looking guy here would reduce to the more familiar V times U to the V minus 1. Anyway, we also get the chain rule by multiple applications of a function of a dual number. So to give an example, if we had, essentially we want this expression to equal sine squared of x, and if we plug that into this formula, we get what we're expecting. We get the primal sine squared of x, we get its derivative, which may again be familiar from various tables of trigonometric identities and derivatives that we saw many years ago when we were at school. I don't know. Okay. Now I'm going to pull the rug from beneath you. I've just introduced that notation, but we're going to change it slightly. But this is going to be leading towards the idea of how we might use this information and then implement it in code. So we're going to use this angle bracket notation. And now, so the product rule, two dual numbers looks something like this. And so we're using the rules that we derived from the first dual number representation. We're applying them in this new syntax. And we could imagine in, say, for example, C++, where operator overloading is a thing, defining a class where we have members that are the primal and the tangent, and then an overloaded multiplication operator that gives us the primal multiplication, and then the tangent, the product rule implementation here. That's this line there, in parallel. Okay, and let's take a numerical example based on this new angle bracket dual number notation. So ultimately, the aim here is not to provide or not to produce symbolic representations of derivatives. It's to get numerical outputs. We're interested in numbers here. So first, let's define an independent variable, x, and its derivative with respect to x is going to be 1, and then a numerical constant c, whose derivative with respect to x is going to be 0. And then let's compose these together. So we've got an addition, a subtraction, and a multiplication. And we can change the value of x, and for every point, we find we've got the value of the function itself, and then also the value of its tangent here as well. So that's the value x plugged into the equation for the tangent to this function. Note that we haven't had to expand this quadratic polynomial out and then do the differentiation manually, as it were. We've got it all happening automatically, and that's my next little point here. This is automatic differentiation. We've defined what the differentiation of addition is with dual numbers, same with subtraction, same with multiplication. Then we're applying these in sort of an atomic fashion in a very isolated way, and we're getting the result for the whole expression. We're getting numerical outputs. Okay, another change of notation. That's fine for the univariate case, but what if you've got many independent variables? Well, now we've got a vector of partial derivatives, something that looks a bit like this, but we use the shorthand with this nabla symbol. And now let's consider a multivariate example. We've got this nice expression, sine of x1 times x1 plus x2, with this computational graph. And so now we get derivatives at every step, and then derivatives at the output, or rather these are gradients now. We've gone from a differentiation arithmetic to a gradient arithmetic. The gradients of x1 are, well, it's derivative of x1 with respect to x1, derivative of x1 with respect to x2, so that's 0. For x2, the conditions are reversed. And then we have rules implemented for the sign and addition and multiplication. And as I change the values of the sliders, we get values for the output, we get, oops, lagging a little bit, we get values for the gradients as well. So there we go. This is multivariate dual number arithmetic. Okay, why is any of this useful or interesting? Why have I spent 12 or so minutes of your time expended that on all that maths and nonsense? Well, okay, so end-to-end differentiability of computer programs. This is fundamental, to gradient-based optimization, which is in turn absolutely integral to contemporary machine learning approaches and more generally mathematical optimization approaches. And so differentiable programming supported by automatic differentiation ensures end-to-end differentiability. And I don't know, you might have heard the words machine learning in that order quite a few times lately. So this is kind of something of a hot topic. And this is kind of the one way of framing what underpins machine learning at the moment. Anyway, more pressingly, what does this have to do with Faust? Because so far we've been dealing just in sort of mathematics and not in audio. So what can we do with this? Okay, so many of Faust's primitive operators we can define in a differentiable fashion. There are arithmetical operators, there are trigonometric things. We know what the derivatives of these primitive operations are. We can apply these somehow. We can maybe implement dual number arithmetic in Faust. We can maybe use a Faust pattern matching feature to provide sort of overridden versions of Faust primitives with the differentiation rules applied. This isn't going to look like it would in a language like C++, but let's see what we can do with it. Okay, and we can then, if we do those things, we may be able to turn Faust, bend it to application in parameter optimization problems. So to do this, what we do is we take a circuit producing a ground truth signal Y. Oh, I've misspelt producing there, sorry about that. Anyway, and then we have an optimizable circuit that's producing an estimate signal Y hat. And then we can compare those two via a loss function. So this little equation describes what's termed an L1 loss function. In this form, it's just saying take the difference between our estimate and our target, and then take their absolute value, and that's going to be the definition of kind of how far we are away from our target with our current estimate. Then the interesting thing here is that if we take partial derivatives of the loss function, and we can do that using differentiable mathematical primitives, then those gradients, those partial derivatives, they represent the direction in which we can move along the landscape of the loss function, as it were, to minimize its value and have our estimate approach our target. And to do that, we have to do something called backpropagation, which you may have heard of, which involves sort of taking those gradients and feeding them back to our parameters and updating the parameters sort of step by step through time. Okay, let's have a look at some examples, for which I'm going to switch to the Faust IDE. I think I have enough time. Okay, so essentially what I've got here is I've written is the code large enough? Should I enlarge that a bit? If anyone, oh, okay, I'll try and make that a little bigger. So I've got this library called diff.lib, which looks a bit like this. We've got I won't go into too much detail here because there's a lot of code and a very small screen, but we have a Faust environment expression here, and within here we've got some definitions of differentiable primitives. So here's a diff add, and a diff sub, and a multiplication, and so on and so on. If I keep going, there's a power, there's a sign, etc., etc. Now I'm setting up some, what I'm going to term differentiable variables. And the reason we have this environment, part of the reason is we pass the variables in, and then we don't have to count them manually. The environment counts how many variables we have, and thus how many partial derivatives for each primitive need to be computed. So if I change this process line, bit of Faust live coding, to d dot, oops, if I can remember how to type, change it to this, we get this nice block diagram representing at the top, this is our primal addition, and then we've got two partial derivative additions here. If I do the same thing with multiplication, this is maybe a bit clearer. The primal is just a multiplication. The two gradient expressions are this product rule thing, two multiplications and an addition. Similar for, let's see, we do a sine. So there we go, we've got a sine, and then its gradients are the derivative of the inner function multiplied by the cosine of the outer function. We can also compose these, so if I do something like, let's see, I'll take one of my variables. I'm going to do vars.var1, and I'm going to take, what am I going to take? That's not what I wanted to do, is it? Ah, yeah, I'm going to do d.diff, let's use a constant ma.pi, and then d.diff, let's do a multiplication. Okay, so now by sort of describing differentiable primitives and composing them in a familiar Faust-like way, I've achieved this, essentially this little differentiable program here, and everything's sort of composing nicely. So we've got this variable. I'm going to try and make the diagram a little larger. That's not really helped. Okay, there we go. We've got a variable, and similar to that diagram I showed you before, we've got, this is our variable. Its partial derivatives are 1 and 0. If we use the second variable, its partial derivatives would be 0 and 1. Derivatives of a constant are both 0, and then these get passed through our differentiable primitives, and that's that. This all happens, as I said, this all happens automatically. Okay, that's fine. We're still dealing with math, so can we do something with audio? I'll try and hurry this up a little bit. So this is a really, really basic example. We've got a target, which is taking a gain control and a DC offset, applying it to an input signal, which happens to be I'm using a noise generator, just Faust's no.noise. And then we've got an estimate algorithm that's built of the differentiable equivalents to the target algorithm. Bear in mind, the target algorithm could be some kind of black box algorithm that we don't have access to, but it's producing an output signal. We can estimate based on the parameters we have at our disposal. Anyway, we're comparing these two via this loss function here, this L1 loss, so that's a differentiable absolute value function. And then I'll describe, so in this particular mode of automatic differentiation, which is called forward mode, the backpropagation step is this recursion. So this is the gradients being passed back from the loss function to our estimate. And now if I, oh, this is already running. So I didn't plug in the audio. It's not a big deal because this one's just white noise, but it's maybe better than just going the whole talk in complete silence. Headphones. There we go. Right, and I can change the, there's another parameter, it's the learning rate. That's how fast how much we scale the gradients by in order to achieve the optimization. But essentially we get something like this, where if I change the gain, or I change the DC, the estimate algorithm finds those values via the gradients that's passed back. If I set alpha very, very low indeed, it's going to take a little while for the gradient to the estimate to kind of catch up. Okay, so that's a fairly boring example. Let's try something a bit more useful. Let's go with an FIR filter. So let's run that. So I've got this bank of filter coefficients. So a FIR filter is differentiable with respect to its filter coefficients. If I start to drag the coefficients around the estimate, again, we're performing a parameter optimization here. We find the filter coefficients via stochastic gradient descent. Okay, so that's an FIR. Let's do an IIR. I'm going to set quite a low learning rate on this one because otherwise there's a risk of the estimate algorithm exceeding the region of convergence and becoming unstable. But if I set this to spectrogram mode, that might be a little more illuminating. So if I start to change the filter coefficients here, we may see there's a bit of ambiguity. There's probably some local minima in the loss landscape here, but if I start to move the parameters a bit more, you should see that things begin to kind of settle down and optimize in the manner we expect, more or less. And so, yeah, you can imagine if we had a nice filter we wanted to optimize on, we could potentially do that with a bank of differentiable IIR filter taps. Right, let's try something somewhat interesting, which is a differentiable delay. So this is now a variable delay rather than a fixed filter tap. And okay, so this involves a little bit of sleight of hand, which is this here is saying take the average, and we're in the time domain calculating loss here, take the average of the last, well, this is going to be 8 samples for the target and the estimate. And then so we're actually able to optimize on the length of the delay line. But if I move backwards, it'll sort of catch up as well. If I go too fast backwards, we exceed the range of the running average, and so this will just fly off to infinity. This is just one of the problems with differentiating delay. Ultimately, you have to make a a numerical approximation in the time domain, and this remains a sort of open question for what's the best way to approach this problem. One way maybe to approach differentiating delays is to model things with, again, with a filter bank. So I've got 2 target delays and I've got an arbitrary length filter bank here. And if I change the delay line lengths, this plucks out the taps in the filter bank that are closest to the lengths of the delays. And interestingly, we can do it with multiple delays. So in principle, we could use this perhaps to model impulse responses. And there are some people looking into this, but not in Faust. So this could be an interesting problem to tackle within the Faust language. That's all the examples I wanted to go through. I have some junk here that was kind of interesting, but I think that's probably, unless we have more time later, but I don't think we have. So I'm going to return to my slides, which are not in a different browser, but in a different tab. I need to do this. Okay, let's just wrap things up. There's also a reverse mode. So all I've demonstrated here was using something called forward mode, automatic differentiation. Now, in principle, for instances where there are more input parameters than output variables rather, reverse mode is going to be more efficient. And this is because of the number of passes through a circuit you have to do. So if for n input variables, you've got to do n passes in forward mode. In reverse mode, for m output variables, you have to do m passes. But if you've got a Faust or an audio algorithm in general that's probably producing 1 or 2 output signals, then you can see that they're almost certainly going to be outnumbered by the number of input variables that we have. However, I mean, there are question marks over this. I mean, this is something that Baydin and Perlmutter and Siskind described in one of their papers on this topic, computational efficiency. The Faust compiler does a lot of things with like 0 signal paths and repeated arithmetic operations and optimization along those lines, which could mean that forward mode in Faust, which well, it works and it's composable, and reverse mode is kind of possible in Faust, I have found, but it doesn't generalize well, it doesn't compose nearly as well, it requires a lot of nested recursion, which is quite difficult to manage. Anyway, it could be that with the optimizations that the Faust compiler does, forward mode is no longer so, doesn't compare so unfavorably to reverse mode, but that needs to be explored. Okay, so far we've dealt with nicely differentiable primitives, except perhaps for the at primitive, which is a little bit of a strange case. for things like floor and ceiling and bitwise operations or selectors, these sorts of things, differentiation becomes less of a mathematically pure thing and more of an engineering challenge. So that's another area that needs to be explored more fully. Yeah, we've spoken about delays and that defying a closed form solution. Also, Faust pattern matching at the present time has its limitations. And so that syntax I showed you, it's nice and composable, but it's quite verbose with lots of d.diff, this and that. It'd be nice to wrap everything in a kind of a forward AD or reverse AD pattern matching function that could then decompose the expression that's passed into it and sort of recompose it in a differentiable fashion, somewhat similar to how the physical modeling library works in Faust. And as I briefly alluded to, this is all loss taken in the time domain. It's not perceptually informed. It really only works for deterministic input. In fact, we're dealing here with pure optimization problems, not with things that generalize, and that's generalization is the basis really of machine learning. We've had some work done over the summer that needs to be merged into the code base, which I'll link you to in a moment in my final slide, that's on sort of turning this approach to automatic differentiation in Faust to machine learning tasks. Essentially, machine learning neural networks are all based on linear algebra, so these are just simple additions and multiplications, and then maybe activation functions with exponentials in. These are all trivially differentiable, but constructing them in Faust, making them generalizable, composable, that's a bit of a challenge. But we have had some work that's been done in that area, but there's plenty more to be done. Anyway, that's it from me. I'm sorry, I think I've overrun slightly, but if you're interested, this is the now somewhat out of date GitHub repository for the experimental Faust DDSP project. And that is all from me. Maybe there's time for a couple of questions. Thank you very much. Are we done? Should we move on? Maybe you can catch me at the coffee break if you're interested. Yeah. Oh, Jan has one.
I was wondering, how did you make
It's not a question on your work that I already know a little bit, but
Oh.
about how you make this slide with the super nice.
I'm so glad somebody asked, because it took quite a long time. What's my favorite one? This one's quite good. Okay, so I mean, the short answer is I used to be a web developer, Jan. So there's some HTML canvas and some JavaScript and some MathJax going on.
Okay.
So
okay.
I'm glad.
So you all did yourself.
Yeah, I mean, I have to give a tip of the hat to the makers of MathJax and all that, the HTML canvas people. Anyway, yeah.
Well, that's super.
Thank you for
super
noticing,
nice.
Jan. Thank you. It's not quite as impressive as the Faust IDE, though. Oh, we have another one. Thank you, Pierre.
Thank you a lot. Very interesting topic. So I guess we could use your library to do some LMS algorithm, the estimation of unknown filters. And
yes.
Does I show your example with FIR?
Yeah,
and,
absolutely.
Do you have idea of the size of the length of the filter we can estimate? And
well, no, that's a good question. I mean, it's not something I've really tried to push in terms of, I mean, it would be a case in my example of, I mean, I guess we could try this now. If we go for the FIR example, that's 8 filter taps. And that runs just fine. If I set this to, I don't know, 128 instead, will it compile? Will it compile? This is maybe a bad experiment to do right now. Oh, it seems to have kind of done its thing. Okay, no, we're getting not a number going on. So there's something awry going on. So the short answer is probably not very far. The longer answer is we need to dig into it. The mathematics is sound, but there's something a little going on for very high numbers of taps. Yeah, so trying to model arbitrary length delays is going to be an issue. But it was just to illustrate that it's possible to model that problem via a filter bank.
That's really nice to have this tool. Yeah. Thank you.
Thank you.
Sure. Well, thank you, Tommy.
Thank you. Okay. Thanks, everyone. Francesco?
So the next presentation is going to be by Tomoya Matsura, and it's going to be on the intermediate representation for synchronous signal processing and language based on Lambda calculus.
Can I start? Okay. So hello, I'm Tomoya Matsura from Tokyo, and I'm very happy to have this opportunity of this talk. So, and my presentation is not actually about Faust, but my language called MEVO, which I'm developing last 4 or 5 years. That is deeply inspired by Faust in the aspect of language design. But I hope it may help finding theoretical connection between Faust and other general functional languages. So today I'm going to talk about the design around intermediate representation for these languages. I named this Lambda triple M. So this is based on the simply typed Lambda calculus. And I'm sorry that I found there were several errors in the paper, and that is already uploaded to the server. And this is the corrected version of the paper. So let's start from the background. There are various programming languages and environments for sound and music, like Maxim or Supercollider or PD, but most of the languages do not have well-formalized semantics. Semantics is here logical description, how the language is evaluated, independent from the real implementation. And one notable exception is in the widely used language is, of course, Faust. And Faust is based on a system called block diagram algebra, BDA, and that combines block with by 5 compositional operators, including recursion. And most of the signal flow can be represented with the constant block and basic arithmetic blocks and delay blocks and the composition of them. And by having this strong formalization, Faust code can be translated into various target language such as C or C++ or LLVM IO. On the other hand, the BDA lacks theoretical or practical compatibility with it of common programming languages. Of course, it is possible to call external C function in Faust, but those functions must be kind of pure, which do not have internal state. So it means that it is easy to embed transpiled Faust code into that languages, but it is not so easy to call the function externally defined in the other languages from Faust. Of course, this is a trade-off between keeping independency as a DSP algorithm and interoperation between various systems on runtime. So proposing a computational model for signal processing based on the other more generic computational model, such as Lambda calculus, has, I think this is a potential to improve interoperability between many different general purpose languages and may facilitate the appropriation of existing optimization method, for example. And one important finding in the Faust is that the most of signal processing algorithms can be represented as the combination of basic arithmetics and delay and the feedback with one sample delay. So I started designing my original language based on a superset of Lambda calculus by adding delay and feedback as a primitive operation. And this is the starting point of MEVO language, which I'm developing this 4 or 5 years. And this is just the small example code. MEVO has a Rust-like syntax design. And this is the example of the one unique feature of MEVO. In the function definition, a user can use a special keyword self that can refer to the return value of the function itself by one sample before to describe signal feedback. And this one pole function is the equivalent of the si.smooth in the Faust that mixes input and the last output with unity gain. This simple example worked in the initial implementation of MEVO, but there was a problem around the use of higher order function and the stateful function. Stateful function, I mean that uses self or delay function, at least one somewhere in the call tree. And this stateful function requires a specific memory space to store or load internal state. And the size for them varies depending on the contents of the function. And the previous implementation had no formal semantics. And if the higher order function tries to take stateful function as an argument, the compiler just emits compilation errors, because the compiler cannot determine required memory space statically. But if we cannot handle higher order function correctly, the language cannot utilize a strong capability of meta operation of the Lambda calculus, like a replicating filter or oscillator generatively. So I started redesigning and implementing the compiler from zero again. That is about 2 years ago. And there is actually another reason for the entire reconstruction, because I was writing the compiler with C++ initially, but I exhausted writing C++ and wanted to switch to Rust. Now the newer version of compiler is 100% written in Rust. And there are several attempts of making a DSP language based on the Lambda calculus under the influence of Faust. And two notable examples is the Chronos and the W calculus. Chronos is based on the one of the variation of high-level Lambda calculus called system F omega, but they don't have no formal semantics. And the other one is the double calculus, which is actually presented at the same session of my presentation of the MEVO 2021. And they are just adding the feedback as a primitive, but they cannot handle the higher order function. And so I started to design my intermediate representation by just loosening the restriction in the double calculus. So the rest of this presentation, I'm going to show the basic syntax and the naive operational semantics of the Lambda triple and fast. But I will keep this explanation as brief as possible, because this naive interpretation of semantics is super inefficient and impractical. So I will focus on the design of the VM and the bytecode design to run this Lambda triple M. In the actual MEVO compiler, I designed a special VM and instruction set, and this translation process from the Lambda triple M to the VM bytecode is not well formalized now. So this is the future work. So in this presentation, I just show the example code and the desired bytecode for side by side. So let's go to the syntax design. So this is the syntax of LAMDA. And in this paper, types of the basic primitive types is limited to their just real number. In the actual implementation, we have aggregate types like tuple, but I omitted in this paper. The LAMDA simply extend call by value lambda calculus with two key terms, just that is delay and the feed. Delay is just a delaying function, and feed is used for referencing prior output of the expression itself. In Faust, maximum size of the delay time is inferred from the term of the delay time automatically, but this inference makes the type system more complex, so I kept the syntax that a user have to declare maximum delay size explicitly, as same as max or PD. And this is the example of the typing rule. And everything is not far from the intuition, I think. The lambda abstraction allows mapping from any type to any type, not limited to number. And delay, the delay time must be a real number. And in feed, because the x represents the last value of the result of E itself, so x and E must be the same time. But I limited, I added the restriction that the type of feed must be a non-functional type. That means in the real implementation, tuple types are allowed, for example, but it's not allowed to contain any functional type as a member of tuple. So if we allowed functional type at feed expression, it means that we can define kind of the function whose behavior changes time to time. And it may be interesting in the theoretical aspect, but it will make the implementation further complex, and I can't imagine the practical use case for now. So I keep this restriction as is. Then this is the semantics, the rule, how do we evaluate from triple. And this notation is so-called big step style semantics, which shows that the pair of the term and the final result of reduction based on the preconditions, but skipping the intermediate process. And a bit unusual notation here is the capital E with small n. And normally, capital E represents the variable environment. It's a list of pairs of the variable and its value at a specific point of the evaluation context. And En here simply means the evaluation context at the time n. And if the negative time is referred, all the variable is implicitly bound with 0. And however, as I said in the scope of this paper section, this semantics is super inefficient because in this semantics, to calculate the value for time n, the value from time 0 to n should be recalculated every sample, and the variable environment are recreated and discarded each time. So to execute LAMDA practically, we should somehow reuse the computational result of the previous time. So from this section, I will explain the virtual machine to execute LAMDA. And this virtual machine is designed based on the implementation of Lua, especially after version 5. This is a register machine, but the register is represented as just the relative position of the call stack from the base pointer. I do not explain the deep. There are many reasons to choose Lua as a reference, but because it has a unique solution for treating closure, which is a common difficult point to implement VM for function languages. And I do not explain this point today due to the time restriction. But if you are interested in, I recommend to read the online book called Crafting Interpreter by Robert Nystrom. And of course, there are many differences between Lua and Mimium. And one significant difference is that the Mimium is statically typed, but Lua is not. And so our VM has more instructions for the primitive operation depending on the types. And I added 3 special operations for treating internal state variables for self and delay. And this is the example of the list of instructions. And note that in the actual compiler, most of the operations have another operand to indicate the word size of the value to handle, for example, tuple type. That is not the single word value, but they are omitted in this paper. And the special operation, 3 special operation is the get state and set state and shift state, and also delay. And I'm going to explain how they work with the example code later. Delay is primitive instruction here, but I think it can be essentially represented with the combination of these other basic instructions. And this is the overview of the actual VM instance and the program, which contains bytecode. And this looks a bit complicated, but it's mostly a normal virtual machine that has, for example, a program counter and the call stack for the function, and the heap storage. And heap memory is just only for the closure in MEVO, because the Lambda triple is called by value basis, and most of the values are copied on the stack. And the all additional part is about the memory space to treat delay and feedback. So let's start from this example. And here we have 3 functions. The one is the FB delay. This is the feedback delay code, which uses the delay with 1000 as a maximum sample size and self. And this second one is a toDelay. toDelay just calls FB delay twice and some. And the DSP function, this is equivalent to the process function in Faust. That is the entry point to the audio driver. And in this code, DSP uses just toDelay twice again. And this is the ideal bytecode for this example. Now I will show how the special operation for internal state work step by step. So let's start from the feedback delay function. And in this example code, VM uses the one global storage to manage internal states. And this storage is just a flat array data. And the storage also has one pointer here called spos, which moves back and forth during execution. And it is moved by the shift state operation. So the second line, we have get state operation. This is the getting the value of self. And when get state is executed, it pops out the value at the point of spos from the state storage and load it into the register. And the third line, we have shift state 1. Shift state just moves the spos by the given value. This time the offset is 1 word, so move it to the false. And next is the delay function. Delay instruction interprets array of data as a ring buffer with a specific size. The size information is stored in the program. And again, after several operations, we have a shift state -1. And within one function, the sum of the offset by the shift state must be 0. Otherwise, the spos moves far away during the execution. And the last get state and set state operation is for returning the value. And before returning the value, we get the self value by get state again, and storing the result of computation by set state. Then, in the toDelay function, that uses the FB delay twice, which calls, so this is the first call of FB delay. The spos moves 0 to 1 to 2 position. And after the call of the FB delay, we have a shift state operation. This shift state operation moves the spos just next to the end of the ring buffer of the first FB delay and calls second FB delay. Then back to the original position in the end of toDelay. And in DSP function, the process is the same. The first call of toDelay moves spos like 0, 1, 2, 3, 5, 4, 6, and moves spos to the 7. And call toDelay again, like this, and move back to the initial position. And the important point is that each function do not need to care about where they are called from, because this offset of the shift state is the relative value. So, and another example is the code that uses higher order function that replicate filter with different frequencies. This kind of code was the initial motivation of the design of this VM. And as explained in the motivation, the size of the internal state variable for the filter factory, given as an argument, cannot be known at compile time because it is passed as an argument. So in this VM, the closure instance, that is the function treated as value. For example, when the function is passed as an argument or returned from another function, they are represented as closure in the runtime. The closure instance holds state storage separately from the global storage. And when the closure called with call CLS operation, and VM pushes the pointer to the state storage of the closure instances to the another stack data to switch state storage between global and closure instance. So this is the ideal bytecode for the filter bank example. And apparently there are no get state or set state or shift state operation here. They are called inside the given filter factory function. And it modifies the storage on the instantiated closures. So the storage for the replicated filter by the filter bank function is allocated on the closure instance. After all, this filter bank function works just like a constructor of unit generator in the object-oriented programming world. So let me show the real example briefly. I just downloaded a high contrast theme for this venue just 10 minutes ago. And we have this filter. I use this multi-OSC. So this is mostly same as the filter bank code, but replicate oscillator, not replicating filter. So if I run this one, I'm not checking the volume. Yes, this is replicating the 20 filter with this replicating function. And if I increase this number by 10, it becomes more complex. And of course, because this is using the higher order function, so we have another example that not adding the replicated filter, but the concatenating by sequentially. So this is super complex FM synthesis using this cascade function. Yes, just this weird synthesizer. So then I briefly wrap up the presentation with several problems of current spec. So as we seen in the filter bank example, MEVO can describe parametric signal graph by executing higher order function in the global context. So this is kind of a unique feature because the signal graph generation and actual DSP is done on the same value level semantics compared to the Faust uses the pattern matching and macro, and Synchronous uses the type level calculation. So this simple semantics will make it easier to understand the language spec for novice users. But there are several problems caused by this unified semantics. So this is a bit modified example of the filter bank function. In the normal Lambda calculus, the variable bound with let expression can be just replaced to its content, because that is equal to the actual evaluation process called beta reduction. So, but this filter bank function will not work correctly. If we run this code, the VM tries to instantiate closures every sample, and internal state variable are initialized with 0 every samples. So this code does not work. It means that the higher order function will not work as a direct replacement of the macro. So users have to distinguish whether the code will be executed on the global context once or executed on a DSP context. I'm going to solve this problem by introducing some paradigm called multi-stage programming in the future. The multi-stage computation is another extension of Lambda calculus that is intended to derive macro features to functional languages without breaking type safety. And in the multi-stage programming, all the macro are expanded after type checking is done. So I think this is gonna be more easy to understand the syntax than type level calculation in the Chronos. And the other point, this is actually a good point, I think, and it is really easy to call externally defined stateful function, just for example, unit generator written in the C++ or Rust. And because it can be called as just like normal closure. And actually, I implemented some external modules with this convention. So the last example, I showed small oscilloscope. This is also implemented with so this is an example of the simple subtractive synthesizer, but it works with MIDI. And this MIDI input and this oscilloscope GUI is implemented as an external module between Rust, and this is the entry point to the MIDI input. And it returns the higher order, this is the higher order function and returns the another function. And in DSP code, we call this bound value without no value. And it returns the value got from the MIDI input. And just the same as the MIDI input, to draw a waveform to the oscillator, we use this make probe function. And this creates a channel to the probe. And we call this probe function in the DSP function. And this value is passed to the GUI. So currently, these external modules needed to be linked statically, but it will work just like a kind of static type version of Lua, easy to embed to the various systems. Back to the slide. Back to the slide. Back to the slide. Okay. So this is a wrap up of my presentation. Now I propose a superset of Lambda calculus as an intermediate representation for the DSP language, and added delay and feed as a primitive. And I also propose the VM and instruction set for it. And this VM has the operation to modify the state space to express delay and feedback operation. And MEVO can express both signal processing and the generative signal graph generation in the same semantics, though the user have to be responsible to distinct whether the execution context is global or DSP. And there are many spaces to implement, of course, and I think I could propose the starting point of the basic execution model of the language for sound and music based on the Lambda calculus. And that is intended to be used in sound domain, but not losing generality and self-extensibility or interoperability between existing systems. So thank you for listening. If you have any questions, just ask me.
Thank you for this very interesting presentation. First of all, how long have you been working on that? Since how long are you been working on that project?
Yes, I'm not working at.
How long?
How long? It's the initial implementation is 2020.
Okay.
Yes, and I started rewriting all compiling from 2020 to 2022, just 2 years ago.
Okay. In the Faust compiler,
Yes.
we have several languages, so to speak. So first of all, we have the circuit language with its own Lambda calculus, so to speak, and then it's translated into signals, and then to the FEAR, and then to the different backends. So I'm wondering if instead of compiling to this, we recently opened the signal and the box API in the Faust compiler. So it means that you could potentially translate your Lambda calculus directly into the signal language of Faust using this API, and then run everything and have all the backends and have all the real-time facilities that we have in the Faust compiler. So it will be, you could have it as an additional front-end language for using the machinery of the Faust compiler, and that would be very interesting too.
Yeah,
maybe.
I think it is possible to translate bidirectionally from Faust to this lam triplem or the lam triplem to the BDA.
Yes, I was more thinking about the signal because the BDA is at a different level. It's on the level of circuits, functions on signals. And here you are describing signals and also function of signal, but it's more signal-oriented than circuit-oriented, so to speak, than Faust, I would say. So this is why I was making this suggestion. It could be quite interesting.
Yeah, I'm going to take a look at the signal API.
We can discuss later on that.
Yeah, thank you.
So Francesco needs 5 minutes to say the coffee break, so we just stay a bit and then we go this place.
But maybe we start again at 11:30 for those people who are online. So so it's going to be a short coffee break.
Thank you.
Okay, so it's easy for me because I just have to do every 2 years, I just have to explain what's new in the Faust ecosystem. So now I'm going to explain what's new since the last edition of IFC. So you have the paper, but now I'm going to explain part of what is written in the paper, and I am also going to explain and present some of the next presentation during IFC, so that you can follow different parts. So tomorrow, last roundtable we will do with Jan a presentation of Faust Consortium and Faust Association. I'm going to speak more in details of development in the Faust ecosystem itself, backends, new compilation option. And part of this will also be explained more details during the roundtable of this afternoon. Widget modulation, which is also a new thing into the Faust ecosystem, will be explained by Jan tomorrow morning. We have some web development, and Michel Biffard, who will come tomorrow, will explain part of what has been done. We have several projects that are now part of the joint work with the Emerald team. Since Graham and myself, I am part of the Emerald team. So there are several projects, and we have some commercial applications that we can speak a bit about. Concerning the compiler, we always try to expand what we can target with the Faust language and model. So we have 4 new backends that have been developed since 22. Several of them are contribution by external people. The first one is Jack's backend, contributed by David Brown. David Brown is basically currently doing a PhD thesis in Faust and machine learning, so a relationship between the Faust compiler and doing some application in machine learning. And for that, he had to try to embed Faust generated code into existing machine learning frameworks, basically. So the Jack backend is a way to go in this direction. This Jack's backend is also integrated into an interesting project developed by David, which is DoDreamer, which is a Python-based environment that allows you to use Faust with a libFaust approach, so you can compile on the fly Faust code and use this Jack's backend, and then you can go into machine learning kind of direction. And you can possibly follow the programmable audio workshop presentation of David on his project. We have the GSFX backend contributed by Joan-Philippe, working with us at Gram in Lyon. So basically, it's a way to target Reaper, which is a well-known DAW. GSFX is a scripting language part of Reaper machinery, so we can now directly compile Faust code to GSFX. There is a tutorial that you can possibly follow on the Faust doc site. We have C major backend. So C major is a kind of rebirth of the Soul projects. You may have heard of Soul language developed by Julian Storer and Cesare Ferrari, who were working on the Juice project. Basically, Julian was the inventor of Juice. And we basically recoded our Soul backend. At some point, I had developed a Soul backend, so a way to go from Faust to Soul. And now we can directly target C major. C major is a DSL, but basically using more imperative language, so it's not the way we do with Faust, but there is a way to do connection between the Faust approach and C major. So basically, the backend means that we can generate
Faust DSPs as a kind of C major node that you can embed into a C major piece of code. And the last one is Codebox Rainbow backend. So basically, Rainbow is a new sub-project part of Max FSP done by Cycling, and they have developed a new DSL for low-level DSP processing called Codebox, which is a kind of extension of the GEN approach. So we are able now to generate Faust to Codebox, and then we can generate also automatically max patch so that you can use this kind of Codebox processing. And from Rainbow, then you can export possibly to C++, max external, WASM, this kind of thing. And we have also a tutorial here. Compiler option. Since we are now working with the Emerald team that I will present just after, we have a project targeting FPGA. And part of what we have done in this area is generate code for one sample processing. Basically, if we want very low level, low latency, we have to compute DSP sample by sample. So it means we have to generate the code in a bit different way. So we have a special option into the compiler, which is a one sample option. We also have into this FPGA project, we need to separate the control from the compute. Basically, control is everything every computation that depends on the change of controller, like sliders, button, can be done outside of the FPGA on a separate CPU, which is ARM in the FPGA card we are using. And we have the compute itself, the DSP computation, the sample audio rate computation done on the FPGA. So we have to separate between the two kind of computation. So we have a new option for that. And we also, in this FPGA project, we need to have a more precise control of memory layouts. So we have a for memory manager option for that, so that we can have different way of managing memory layout, putting part of the memory on the FPGA, putting the other part on the ARM, and exchanging with a shared memory between the two things, the two CPU. About web-related developments, we have rewritten everything in TypeScript. So the glue between the Faust compiler and the way we use the Faust generated code in the web, which is basically the web audio node API, we had that in JavaScript, and at some point it was time to rewrite everything in a more modern and controllable language like TypeScript. So it was done. And from this, we basically separate as a Faust WASM project, which is basically embedding the libfaust compiler compiled to the web using mscript compiler, so in JavaScript and WebAssembly, and the additional glue code that we need to use this to become the DSP part of web audio node, Faust generated web audio node. And using that, we have reworked all of our web tools, like the Faust IDE, Faust Editor, Faust Playground, and we had the help of Jan Klester during a Google Summer of Code last year. So he was able to use this new machinery. So it's kind of transparent for user, but for us, it helps a lot to simplify and maintain this kind of thing. And one interesting consequence of that is that we can also obviously do a kind of static compilation with this machinery, and we have developed recently a way to export a statically compiled Faust web audio node as a progressive web app. And you can look at this faust.gram.fr. We have some of our old smart Faust projects that allows you to create kind of small instruments with sensors, accelerometer, gyroscopes that you can deploy on your smartphone. And now you can do that completely using the web platform, basically. So you can possibly install this on your smartphone. And there is another interesting development that was done by Jan Klester during this Google Summer of Code, which is a Faust web component. Basically, the idea is that you have a new tag, which is Faust editor. You can just put a piece of Faust code, or this will open an editor, and this version is just the widget with the GUI. And well, assuming that we embed this piece of JavaScript code, then you can have this kind of nice looking use of the compiler. So for instance, here we have every piece of code is using this. So basically here you have this Faust editor stuff, and behind you have the Faust compiler running, and you can just I have to. So you have the bell here, and you have the SVG dynamically compiled and all this stuff, which is quite nice because now we can have every, like the workshop. Every workshop we have or the tutorial we have everything that you can test directly into the website, which is quite nice to have. We have the web audio module project with Michel Buffard. He's going to explain that more in details tomorrow. So a way also to use Faust to generate the web audio module format, which is a kind of VST for the web project. With the Emerald team, so Graham is part of the Emerald team. Emerald team was a way to connect with the academic world in Lyon. So this is something we had in mind at Graham since a lot of years, and the project was able to start in 22. So basically, we have three partners: Graham, the City Laboratory, which is a laboratory in the Lyon Doua campus, and INRIA, since now Romain Michon is working on INRIA, and also Yann Orlaré is working at INRIA. So Emerald means embedded audio system, and we are basically working on several subjects, but as you understand, on embedded systems like the FPGA project. So trying to use Faust to compile directly for FPGA-based audio boards. So the project related to this compilation on the FPGA board is called CFALA, which is basically a compilation chain, a full compilation chain going from Faust or C++ up to an audio card using FPGA. And we basically use an additional tool, which is HLS, high-level synthesis from Xilinx. So it's a compilation chain that you have to use if you want to target FPGA. Basically, you use kind of adapted C++ code, and then you have this compiler directly generating VHDL code for you, starting from this adapted C++. So we go from Faust to this adapted C++, and then from C++ to VHDL. And all this stuff is now more or less completely automatic using the Cipher chain. During this work, at some point we understood that the Faust generated code was not the way the FPGA wants the code to be. So we also did some experimentation directly writing things in C++, like when designing FEAR and ER kind of filters. And the point is that when we understand how we have to use C++ to express the code in the way the good way for the FPGA, then we can get back this understanding to improve the Faust compiler for this kind of very specific CPU, which is the FPGA is really different compared to a regular CPU. So if you want the code to go fast on the FPGA, you have to shape it in a very specific way. So we try to move from experimental uncoded C++ back to the Faust compiler. And Jan is probably going to say something about that during the roundtable. We have also more engineering stuff done in the MEVO team, like running a regular Linux operating system on this Zibo board. So basically, we are using this Zibo board, having an ARM CPU and the FPGA, and on the ARM, we can deploy a regular Linux system. It means we can reuse part of what we have developed in the Faust ecosystem so that we can control audio running on the FPGA using MIDI, OSC, and regular GUI, just by reusing codes that we already have, which is very much easier to use compared to the old system that was kind of bare metal operating system. We, as the MEVO team, has also developed an audio over Ethernet protocol, allowing to exchange from a laptop using a Jack client up to the Linux running on the Zibo board, and then to the FPGA. So we have a full multi-channel audio system that allows us to do this kind of setup, which is part of the machinery we need for several multi-channel audio projects around spatialization and this kind of projects. So we have also developed two sister 32-channel audio board to be used with FPGA machinery. And part of this is explained on the website of the MEVO team. And you can have a look at what has been done with the Plasma project, which is a joint project with Karma and managed by Roma and other in the MEVO team. And for instance, one project we did with this sister 32-channel card is a wave field synthesis setup that we can use. We also try to directly generate VHDL code with a Faust to VHDL tool. It's very difficult. We have a direct Faust to VHDL backend, which is connected in the signal layer into the Faust compilation chain, but it's quite limited for now. We also are working on using fixed point format instead of floating point format when we target FPGA, because floating point formats consume a lot of resources on FPGA. So using fixed point is a way to limit the resource you use for each mathematical computation. The way we do that is by extending the interval annotation that we have in the Faust compiler with floating point precision. And well, we had a postdoc, Agateru, working on extending the interval library, which is part of the Faust compiler, so that we can annotate each of the computation step with the needed precision if we switch to fixed point by having the MSB, LSB information for each of the computation part in the computation graph in some sense. And this is going to be used if we use the Cifala compilation chain or the Faust 2 VHDL. It's still not in production because it still has some limitations. So it's probably usable in very simple use case. Commercial application, we have, now we can say publicly that Noisy 2 from a French, assuming it will open. So it's very nice synth, very expressive and well heavy synth from Expressive, which is also developing hardware controllers. They are developing the Touché multi-axis controller. They are now also developing Osmose, which is a very nice keyboard with high sensitive keys. And they are now going to develop their own DSP modules. And Noisy 2, for instance, is almost completely Faust-based, which is very nice. So we help them to optimize the code and at the Faust level and at the C++ level. They also have Archer, which is another project. It's a physical model of string, so viola, violin string. And the nice thing is that first it was written in C++. Now they have the new Faust version, and it's the new Faust version allows them to extend the model more easily than it was the case with the C++ version. Another project which is nice is a small company named Punk Labs. They have developed, like now they have 6 audio plugins. And the thing is that they are using Faust targeting Rust, and then they are developing the architecture part of the application completely in Rust and using another framework which is now appearing into the Rust audio community, which is NEH plug. And so they are now using this way of developing plugins, which is obviously interesting to follow because, as you know, Rust is supposed to be the new low-level, safer language to do all kinds of things, and in particular, audio developments. So you have a very pushy Rust community. And since we have this Rust backend in Faust, we can have this kind of project appearing. Ecosystem, as usual, I'm taking part of my time maintaining the ecosystem, the Faust site. We have this powered by Faust page that I regularly enrich with new projects. So we have now more than 220 projects using Faust in different ways. This is also a way to get some piece of interesting already written DSP when you have an open source project, which is the case for a lot of them. The documentation, the libraries, always improving the libraries, merging pull requests from several people, improving the libraries. And we have the Discord channel, which is a way to have a more instant feedback with the community. And that's all for this first part of my presentation. And next part will be during the roundtable. Thank you. everything is clear.
Then we take out the microphone when the performance is starting. So I'm Domenico Cipriani, and now I'm performing this experimental performance that is called Move Float, that is music on the fly with level of details. This is a joint project of the EVREF team of INRIA in Lille, that they are the core group behind Pharo. I'm using Pharo, and the Mint team of Crystal, always in maybe better. And Mint, they are researching on human-computer interaction. Okay. Okay. For the performance, I'm using Fausto. Tomorrow there will be a workshop about Fausto. Fausto basically is a API and library to use Faust inside Pharo. So we have an embedded compiler. I will talk tomorrow more about the details of Fausto. And for today, I just ask you to watch the performance. And at the end, if you are so kind, the question doesn't take so much time. Probably we are trying to write a paper for NIME with the result of this performance. Yeah. So. Needs a little bit of setup. Vuoi essere sound? C'è qualche suono che arriva? Vediamo, allora vediamo adesso. Vabbè, dobbiamo farlo partire, poi vediamo. Ah, ok. Thank you. Okay.
This is how you shut it down.
I thought it was nice to end with a lot of debugger opening and see how it was when I did it the first time. So this time was a little bit on purpose. Yeah, because basically you have a debugger when you have an exception, opening a debugger in Pharo, and is opening another one for every loop, and you cannot stop that if you don't make a safeguard before. Thank you very much.
Can you hear me? Okay. Sorry for the delay, and we had some technical issues at the last minute. Everything worked previously, and then we had some plugs unplugged. Okay, so we lost lost power and so on. So just to give you a brief introduction on what we're doing today, as you can see, we have an orchestra there. There are 17 musicians playing. At the moment, there is only one, but afterwards there will be all 17 playing. It's from Poland, in Wrocław. Okay, so they are far away. It's more or less 1,000 kilometers from Turin, where we are now. What we are doing in the current, let's say, event is the following. We have a system which is designed for audio, which is on that side, using an audio card with 4 outputs and a Raspberry Pi. The system is designed for network music performance, okay, so playing together online, and we are using the same system on both sides to communicate together. Why we need some system like that is due to the latency. We experienced already this system and the latency that it has, and it allows actually musicians to play together in both sides. What we do today is something different though. So what we have at the moment is just a sort of introduction on this kind of concert where there is the musicians called Olgerd doing these 4 let's say these quadraphonic output from the laptop and so on. Afterwards, we have a conductor, Kasia here. She will be conducting the same orchestra, but from here. We will do a remote conduction setup where the idea is we are using a VR headset, which is there. We will use it after, as soon as he finishes with this piece. And the musician on their side are able to see her through something that we developed, which takes advantage of WebRTC for the communication part, which means that they can see using just a web browser. What we did here at the bottom right of the screen is a sort of preview of what she sees within the headset. Let's say in a reduced version, she on the headset also has some additional things related to control or to, for example, seeing the music score that we won't see, okay? Because it's not exactly the same thing that she sees, it's just a replica, which uses the same technology and communication of musicians in Wrocław, just to give you an idea of what they see. So as soon as this piece finishes, we start with the conducting, and we will show you more or less what's happened. A big disclaimer on top of everything is this is very experimental also for us. It's the first attempt, yeah. First time that we use this kind of technology in this scenario. We have never tried it before. She was not able to try it before because yesterday we had all kind of issues. So it's a first attempt with remote conductor orchestra, which is 1,000 kilometers away. So that's something that we have to introduce you. I will leave you now to this music, let's say, first piece, and then I hope you will enjoy it. If we experience some issues, please be patient with us. Don't complain too much. I hope you understand that it's experimental. Okay. Thank you for the attention.
Serdeczne gratulacje dla dzisiejszych wykonawców oraz dla pana kompozytora, którego teraz proszę, aby zabrał głos.
Dzień dobry. Bardzo serdecznie dziękuję za przybycie na dzisiejszy specyficzny i specjalny koncert realizowany w eksperymentalnej technologii MEVO. Dzisiaj mieliśmy zorganizować próbę, ale tak się zdarzyło, że dzisiejszy koncert był zagrany a vista niemalże. Nie udało nam się przegrać od początku do końca w całości przed dzisiejszą
That was our first try to play together Turin Wrocław.
Wszystkim wspaniałym wykonawcom, którzy
He's
stawili
saying
czoła
thank you
przygotować się
for
w tak
the
krótkim
players, for the musicians and for everybody.
Jest to chyba jeden z ostatnich projektów, które organizuje na Akademii, przynajmniej jako student.
It's his last
project bardzo
in that academy.
Przy tym projekcie pracy
Because he's finishing his studies there.
Organizacyjnej, żeby przygotować wyjazdy dla uczestników, dla dyrygentów, którzy pojechali do Turynu stamtąd realizować ten
He's
koncert.
saying about us, conductors.
Były
We are
przygotowania
here,
do koncertu,
group from
oczywiście
Wrocław.
partytury,
We are on
nuty,
Erasmus
cały ten
program.
system. W dalszym ciągu część rzeczy jeszcze się nie udało w 100%, ale to przy przyszłych
Not everything was
wykonaniach
perfect.
na pewno wyjdzie. Cóż mogę więcej powiedzieć? Bardzo dziękuję.
Thank you.
Tym
Thank
koncertem chyba podsumowałem 8 lat studiów na tej akademii.
It was his
Także
summary of
dziękuję
his
bardzo
studies.
serdecznie i jeszcze raz wszystkiego dobrego.
Greetings. I don't know. Sorry, I'm not a good translator.
Jeszcze raz ponownie W imieniu wykonawców i kompozytora dziękuję Państwu za przybycie.
Thank you
Do
very
zobaczenia.
much for coming. Yeah, and that's it. That was that. Something else? I think that's it. in front of that.
So thank you so much. So just to give some context, so this piece was composed appositely for this occasion, and we are hosting these 5 students from the Karol Lipinski Academy of Wrocław in Poland. They are all studying conduction, orchestra conduction, so they are helping us testing the system. So these days they are running some tests with us, and we are trying to understand what has to be improved, what we have to develop further in order to have a smoother interaction, etc., etc. And their feedbacks are very, very, very valuable. So thanks to you all for participating. Thanks for all the stressful rehearsals you had yesterday and today. And thanks to you for your patience and for listening to this performance. Thank you.
Hi, sorry. Okay, so if you have any question, any comments, just to mention something, probably you saw that sometimes Olga, the one that composed the piece, sometimes stood up because we had some issues with someone. Yeah, we're not connecting. So we think he was going there just to make sure that they were attacking on time. So just to answer that. If you have any question, feel free to ask. Anything from technical to curiosity to anything else. We are here. Or if you don't, that's fine. It's fine. We are not like here asking for questions. Yes. Turn it on. Just the. Okay.
Okay, first of all, thank you for such an amazing performance. It was a pleasure, like 100%. Thank you so much. The first question is, why is it important to have a VR system here? Why you can't just use, like, I don't know, like the video itself? Why is it important to have a VR?
Okay, so if you think about the VR, we have an advantage with respect to video, which is the fact that she was able to point directly to each musician. So each musician has a personalized view from their point of view. So they are able to identify, for example, she's pointing at me or not. With a video, with a camera, you cannot have that. You either have multiple cameras, but it becomes not feasible at that
So
point.
the musicians, they see the thing we saw from the VR part.
I can show, the best thing I can do is show you what happens from the point of view of the musicians, which is the following. When you start as a musician, this is what happens. Hoping that it doesn't crash. Just a second. A bit of pressure of writing passwords by. Okay, so this is what they have. They select the role in which they want to connect to, and let's hope that they. My bad. Now you can see. Okay. So the idea is they have this page in which they select a role, and when they select a role, for example, in this case, let's select something like I don't know, maybe the electric guitar. It loads the application for them, which is a web application, and they see it from this perspective. If we open another page, just a second, I need 2 hands for that. So imagine that we're now connecting with another musicians, and in this case, let's select, for example, the violin and viola, or is it the same that I selected here? No, okay. So you can see if Christina now points to the violin and viola, you can see that here they can see that she's pointing to them, but here she's pointing to someone else. Okay, so the reason why we selected to go for VR headset was to be able to track the hand movement and have this personalized view. For the representation of the avatar, instead, we decided to go for web technologies for the ease of, for the musician be able to open the web page, they see it there. They can also use tablets, which some musician did. And so each of them, let's say, the disposition was similar to how were they were like disposed in the location there. So they saw the conductor, let's say, as if it was in front of them, pointing to each of them individually. Okay. Yes.
Okay.
In this case, each musician had either a laptop or both of them worked, and each of them opened the web browser and just saw that. So we think they had the music score, and close to the music score, some way to see this screen or this browser in this case.
Okay, another question. Which kind of technologies did you use? Like, is it only pure Unity or maybe something else?
In this case, it's Unity for the part of the design, both in the headset, because that's the thing, the environment that was supported, and also for the design of the interface here. And for the communication part, instead, we are using WebRTC to be able to send data from there to here. There were some issues related to the headset, to the connectivity of the headset. For example, with headset from Meta, which is the one that usually you find easier, they support Wi-Fi as a connection. With Ethernet, we had some issues. And in the end, what we decided to go for was a sort of setup in which we connect a USB, we send the USB through the USB data to the Raspberry Pi, which was using a Node.js application, using under the hood a way to communicate with WebRTC and sending the data to the browser. With WebRTC, we had the advantage of being able to create this peer-to-peer connection and send that data using UDP with peer-to-peer, which means that it was, let's say, it should have been better from the point of view of the latency. The issue is that we still had some latency related to the tracking of the hands. And so it was not like zero latency, there was some latency, and we wanted to see if it was, let's say, good enough from the point of view of being able to conduct, and also from the point of view of the huge delay from the point of view of the headset and the tracking and so on, while having a small delay on the audio. Okay.
Another one, thank you so much. Was like the peer-to-peer connection enough for dealing with latency or not? I mean, maybe you did something else in order to deal with it.
From the point of view of the asset, we didn't do that much because we cannot do that much. Meaning that one of the main reasons why we had latency was the headset itself. It introduced latency for the tracking and so on. Since the headset is really like close from the point of view of development of what we can do, we could not do that much. We tried to enough way with all the latency we could control, but there are still latency introduced by the render in the browser and by the tracking in the headset. If you think about the fact that it's camera tracking the hands, and then there is a neural network, we try to predict where it goes and to detect the different fingers and so on. The latency there was already high enough that the other parts were not so important to optimize, because with respect to the latency introduced by the headset, they were minimal, let's say. But peer-to-peer worked. The only issue is, again, you have WebRTC, and not all the times you can create peer-to-peer connections. So in this case, we also had a relay, and the relay may have around 20 to 40 milliseconds of latency. Okay. So,
okay,
yeah,
thank you so much.
If you want the number, I think we had around like 120, 160 milliseconds for the just the application layer and so on, plus the network. Okay, so I think from the point of view of the visualization, luckily, let's say we were around the 200 milliseconds ballpark. Okay.
Thank you.
Are there any other questions? Okay. Does not seem to be any other questions. So thank you again for listening to this. We're really happy for that. And that's it. Thank you.
Next is the workshop ABC. So Alain Bonardier and Paul Gutmann are going to present us the ABC open source library written in Faust. which allows to do synthesis, multi-channel ambisonic processing, and using Max MSP or Pure Data as a distribution frameworks.
Can I plug the audio? Hi, I'm Paul Gutmans, researcher, French researcher based in Paris 8 University, and my colleague Alain Bonardi, professor at University Paris 8, and he will present abc.lib library designed for spatial audio processing and multi-channel processing, mostly for mixed music, written in Faust and distributed as a Max package and Pure Data. Today we will mostly use the Max version, and if you don't have a Max license, it doesn't matter because you can download it on this website of Cycling 74, and we don't need to save anything, so you can use it freely.
I have all the installation, this small disk, so I can pass it to you where we find the installer for Max for Mac OS and for Windows, and our library as well. So if you need it, just ask. This is a workshop. This is not a course, academic course. So we can interact, of course.
So if you have questions,
don't hesitate.
Interrupt us. Yes, yes. Version 8 is okay. We didn't try with version 9, so version 8 is okay. And if you want to, yes. It's working for Linux and Pure Data, but today we will not use the Pure Data. But our library is distributed for Pure Data Linux, yes. And we will talk about that in a few minutes. But all the examples will be on Max. Yes. Okay. If you want to present, okay. So we will start with an overview of the library, on covering its issues and the architecture, the different compilation pipelines, and we will present the two distributions, Pure Data and Max. And we will focus on the Max package because it's We have finished a new version of the Max package, and we will dive into examples first in a multi-channel context and then in ambisonic contexts. And I don't know if you want to present the context of the library.
Thank you. So I would say just a few words because the essential of this workshop is to manipulate and try things by ourselves with you. And our context was is because we are in our research team, research and creation team. We have a long tradition of working on spatialization, especially ambisonic spatialization. Many of you know about the HOA library that was started in 2012, 2013. And it was at this time a C++ library that was implemented for Max, PD, open frameworks, Unity, etc., etc. And it was added some interfaces for spatialization, 3D HOA, and this was used. I remember we had something like 20,000 different downloadings from people all around the world. And unfortunately, we came to first the drastic changes in the architecture of PD, of pure data, which made our development obsolete. And you know how, in France at least, funding of research comes by projects. And you submit a project and you get comfortable funding for 3 or 4 years. And you develop an environment, a software, etc. And it's very difficult, I should say even impossible, to get some more funding for the maintenance or for the upgrading of the former development or former project. So we were very sad about this obsolescence for PD, and without having any possibility of funding to hire a developer to redevelop the PD version, for instance. And concerning Faust, and you will see the connection with Faust language in this slide, because of course we deal with spatialization, HOA, etc. But we have been teaching Faust language for many years, and teaching it in a framework of programming languages for computer music courses, licensed courses. And as well, we teach Max and PD, of course. And for instance, in PD courses, we use sometimes, because they are the same students, we use FaustGen objects to include Faust codes into pure data patches, because we think it sounds very well. It's very interesting to write some with the students to write some sound processes that have a kind of perennity and are explicit because you see the code you are producing. You can read it, reread it, and come back to it later. And we also use it for master classes in the framework of mixed music class with Jérôme Combier, our professor of composition, and of course with the PhD students, as Paul has done, for instance, in his PhD until he got his PhD in May, and he used a lot of Faust inside his research and creation.
And ABC regroup all this history of HOA library and all our teaching program in Paris 8 University, all our patches, we translate them in Faust in order to periodize and yes. Okay, about the architecture, ABC is most of the functions of ABC are graphic functions. You can see an extract of the code, just a V slider or H slider, and a few arrangements for musical adaptations, and those functions calls processing function in 3 other library which we develop, mm.lib grouping DSP function for multi-channel processing and mixed music utility. ABC Sounds is a collection of audio file, and HOA2.lib is a parallel version of HO.lib. Just it's an ambisonic library, and then we have a collection of shell scripts which generates all the DSP for all orders ambisonics until the order 7. Various instance numbers for all the multi-channel processes, and in parallel we have scripts which generate DSP file with all the dependencies in order to be used with Faust Gen in Max and Faust Gen 2 in Pure Data. And for the Max target, we have 718 situation. We have only 55 family of function, but we compile them for many situations, many loudspeaker setup, many number of instances, and in order to have a stable version for Windows, we pass through Rainbow. So we use the Faust to Rainbow command, and then we use JavaScript in order to add in all the Rainbow patches some boxes to make OSC communication between the script and the patches. And we compile one by one all those patches, and after 35 hours, we have our 718 externals, both for Mac and Windows. Then we use JavaScript again to create patches and add all the externals in order to see if there are some errors. And well, we have our well-suited package following the Cycling 74 recommendation. And for Pure Data, if you...
Yes. So for Pure Data, until... so maybe we could show the GitHub repository so that you can understand, see where our last version, our Max package is, and what was in the past. Until version 1.0.6, we used to compile, it was complex. I will not blame Stefan, of course, because there were Faust compilation towards several targets for Pure Data. Pure Data for macOS until Mojave, and then after Mojave, macOS system, and for Windows 32 bits, and not on PC, on Windows, and no version for 64 bits. I know there are good reasons for that, but as Paul has shown on the slide, we were and one version for Linux, so we had 4 versions for pure data, and it was a bit complex without being able to provide a Windows 64 bits version, which was the main. Let's say our students, half of them have PCs and they work on Windows, and they ask for they like to practice on pure data, and they would like to use our library on pure data with Windows 10 or 11, so it means 64 bits. So our idea was now for pure data to have only one version, and using Faust Gen 2 that was developed by Albert Greff, and which provides solutions for it's available for macOS, Windows, Linux, etc. And we'll see if we will implement or not a wrapper, as Paul will show in the Max version, but it's a good idea. The only problem I have to mention here is I exchanged with Stefan, with Albert this summer, and Albert says he doesn't have time to update regularly the Faust Gen 2. It's a shame, in fact, because for the moment, the last update it was done in January 2023, so it's more than 1 year and a half, and it becomes to be not so updated. And for instance, there are some recent functions from Faust which were added to the libraries that are not compiled, and that make create errors. So we need we would like to have a permanent solution for pure data. It means an embarked, embedded Faust compiler inside pure data. So we had a PhD defense in our lab 2 days ago, and Miller Pocket was in a jury. So we ask him if he would like for next versions of pure data to include Faust Gen, an embarked Faust compiler. I'm waiting for his answer. He says, okay, we'll see, and why not? So I will show you what happens now on pure data. What used to be before this 1.1.0 version, it was classical non-multi-channel implementation. For instance, on the left, you see what happened with external compilation, online or local compilation. It means, for instance, I compiled multi-encoder at ambisonic order 3, enabling to position in space 4 sources. So you see the syntax is ABC, 2D, multi-encoder 3, because we are at ambisonic order 3, and 4 sources. And I just put a quadri player with enabling to play I don't know, any quadriphonic wave file. And we had what was interesting in the, for instance, the online compilation. It would provide the two things: the PD Darwin compiled object on the left, and the as well as the Canvas version, which is the version looking like a VST plugin with the user interface directly proposed and generated by the compiler, which is for beginners in pure data and for beginners in Faust, very, very interesting to learn, to understand what happens, because they send messages to set the values of the parameters, and they see directly the sliders moving, etc. And they can listen for the people learning these languages. They can directly see and listen what they are doing, and it's very fruitful in terms of pedagogy. And on the right, it's just the DSP file, the same content at the beginning, but it's using Faust Gen 2. You just type the name of the DSP file, which is the same but without the tilde, and it just directly compiles inside the patch, and you get the impression that it is like an object. And when you double click on this ABC 2D multi-encoder 3.4, it opens your preferred editor, and you get the Faust code, and which is very convenient as well. And this is just to show what the online compiler automatically generates with the user interface and all the very interesting also to have the presets. When you implement a slider in the code with a starting value, you get this starting value in the user interface, and you can, with the bang, which is at the top right of the interface, you come back to the starting values of your plugin, and it's very, very, very convenient for beginners. And this is what we are moving to, multi-channel now. We can see as professors with students, everything goes faster to make patches. It means now students, in the past, we would show patches, make patches on our side and saying, okay, we work on stereo, etc., because you only have stereo at home or headphones, etc. And we will not show you octophony and quadrophony, etc., etc. Now there is no excuse. You can directly work on multi-channel ambisonic situations with a lot of channels, and the implementation of multi-channel in Max and Pure Data now makes it very easy to make a complex patch with polyphony. I think the main musical idea is to implement polyphonic processes, and to make it without losing your time, wasting your time to connect things with a lot of connections. So now one connection, steps of process, which with one object, one connection to the next object, one connection, etc., up to the DAC at the end. So what you see in the left is what was implemented and discussed, because we changed last summer. We changed modified I can't remember the name of the developer who did that. You remember? Christopher Resi, yes, we exchanged with him, and he added the opportunity to compile to multi-channel, having a very subtle system. If you add -m to the end of the object, you get the multi-channel version of the object. If you don't add it, you still use the former version, non-multi-channel version. So this makes retrocompatibility very easily, and you can keep your old patches, etc. And you can move very quickly to multi-channel implementation. And on the right, this is what we should get for the Pure Data version of ABC. It's a multi-channel version based on Faust Gen 2. It means we have, thanks to we have written some Python programs to generate abstractions presenting things as multi-channel. So these are abstractions. We keep the user interface on one side, and with -m-ui, and we with only or underscore. It's underscore, sorry. And on the left, _m to get the multi-channel version, and _m_UI to get the multi-channel and user interface version. And yes, we just mentioned the Python scripts and programs that generate all that automatically.
And yes, we think now that the solution of FaustGen is the future, because FaustGen work on all the systems and it will be easier.
It is easy. It's easier, but we need regular updates of FaustGen to be able to include all the new functions and developments that the community provides to the Faust ecosystem.
And the particularity of the Max version, which is includes many new features in the new version, is the use of the wrapper developed by David Pharo and graphic user abstractions and well-defined documentation and reference pages, which facilitate the usage. And why we need to use a wrapper? It's because we have 718 externals, but we have, in fact, only 55 function which we need to use. So, in order to simplify the life of the user, the user don't call the binaries, but abstractions. In those abstractions, there are JavaScript, and those scripts generate all the patches inside those abstractions, and all the help patches and reference are attached to the abstraction instead of the max binaries. For example, very simple example, we have a multi-channel process, which is the gain process. Simply, it's just a multiplication of signals. And in the context of a free-channel multi-gain, we have the external ABC_gain free tilde, but the user don't call that. He call the abc.mc.gain tilde abstraction, and the first argument is the number of instances. And inside this abstraction, we have the JavaScript, which generates the right patch called the right external, depending of the name, the attributes, and arguments of the abstraction. Because we want to shoot with the max usage, because when you use max, you don't change the name of a box if you just want to adapt the function. For example, if you want to use a packing function, multi-channel packing, you use mc.pack tilde, which pack single signals in a multi-channel signal. And if you want to pack three signals, you call mc.pack tilde free. The first argument you write free, and if you want to change that and pack 5 signals, you just change the argument with 5. Okay, so we can move on the demonstration. And if you want to download the library, you need to go on the GitHub page. In a few days, few weeks, you will be able to download it directly in the Max package manager. We are in discussion with the cycling team, and we give you disk and USB if if you want to make the patch at the same time as us. So if you have downloaded the library, yes. Is that? I can make bigger thing. Okay. So on the GitHub of the library. Okay, so when you have download the library, the pack, I have it on my.
It's 1 GB.
Yes.
Yes. Only, so if you download it, you are not from.
We have it on the small disk here.
Yes, it's a limitation because we need to compile each function for each situations. For example, for multi-channel processing, we compile for 1 channel, 2 channel, 3 channel, and etc. And so we have a package with 700 externals for Mac and 700 externals for Windows. And the second limitation is that, for example, when we use ambisonic decoding, we compile it until the order 7, and for 16 speakers maximum. But if tomorrow I will go to a theater with a system loudspeakers setup with 20 or 30 speakers, I need to compile a new object and add it in the package, etc. Okay, so if you download the package and you can put the folder inside the package folder of Max 8 here. And we can go in the package manager, see our installed package, and go on the welcome patch, explaining the context of the development, and dispatch send you on 8 topics patches, which is not tutorial, but grouping those patch group many example of situations. For example, for the first topic, we have all the ambisonic utilities, encoders, stereo encoder, multi-encoder, it's just encoding of many sources, decoder situation, optimizers, and we have, as you can see, many ambisonic utilities, but also multi-channel processes. Here with synthesizer, sequential delays, harmonizers, frequency shifters, granulators, flangers, and multi-channel reverberator. Okay, but in those patches, you don't have any explanation. If you want more explanation, you need to go on help patches of all the abstraction, and here you have explanation with more details of what each object do. Okay, so the advantage of the well documented package is that for the user point of view, when you write ABC dot, yes, okay. When you write ABC dot, you see here, it's maybe too little for you, but you see all the abstraction of the library. And you have a little explanation, digest explanation of what this abstraction do. And for example, the taxonomy is ABC, the name of the package, MC for all the multi-channel processes, HOA for all the ambisonic processes, and we have some utilities like scope, quadriphonic output, or multiplication by 2p, which is out of the big family MC or HOA. For example, we can make a simple additive synthesizer and like that. And you can see if you click here that the argument of the multi-channel objects is the number of modules in parallel. So if I want to have an additive synthesizer with 16 sinus, it's just like that. And if I want to know how to use this abstraction, we just go here to the reference menu, and we have informations about the messages and the attribute of the abstraction, because it's not an object. As if I double click, I see here the JavaScript which generates the patch with the good external and etc. Okay, and okay, so the first, if I I can choose a fundamental frequency of this synthesizer, which is the F0 attributes, for example, 2020 Hertz. And then I can choose to use a panner, a Shawning panner with 16 inputs. The wrapper, all the abstraction have, not all the abstraction, many abstraction have two inputs. The left inputs is for multi-channel signals, and the right inputs is for control, just control. And then I can use a graphic abstraction to all the graphic abstraction of the package. If you want to use attributes with those abstraction, you need to go in the inspector. And for example, this abstraction have an attribute which is the gain, the initial gain of the abstraction, and you need to go in the inspector to set this attribute. Okay. Be precaution. Okay. You can put it down. Okay. If I take the, you can cut the audio, please. Okay. And you can, yeah, it's okay. Okay, so the Chopin is taking each sources. Here we have 16 sources, and he spread it in the stereo. And here we have the stereo signal. But we want to have a little bit of temporal action in this sound, because for now it's very static, and we can add some random envelope, like to have an effect of granulation for 16 line, and we have two type of random, linear or cosinus. It's not the random, it's the envelope shape. Sorry. Okay. And this abstraction we can change the frequency of the random generator, and we have a variable which is the rarefaction. If the rarefaction is like 1, we don't hear any sound, and if the rarefaction is 0, we hear all the sound. Okay, so
I think the rarefaction is what Pierre has shown this morning with Jose Miguel granulator. Kind of, one, if we go to 1, no sound at all, the granulator is not chosen by the random process, and 0, it's always chosen, something like that. So.
okay, and maybe we want to add some reverberation. abc.mc, no, just reverberation for. And our reverberator have 2 modes, stereo and quadrophonic. Okay, and for the duration, we see here that we can set the duration between 0 and 127 to suit with the MIDI format. Okay, so for example, that. Okay, and here we can change the situation very easily. If you want to use quadrophonic, for example, we can choose to separate those signals. Oops. Use ABC, MC, Chopin 8 here and 8 here, and then you can use abc.rev for mode quadri. Rev du. Need to combine those. Okay, and we have a graphic utility for quadrophonic output, abc.quadri-out, and if we are connected to the quadrophonic system, which is not the case, we need only to connect that, and it will work. Okay.
In fact, since we started using this new package since the beginning of this academic year in October. And we could see for our students a really drastic change in the practice of Max. As you've seen in a few minutes, we can implement a multi-channel process, something playing, for instance, in our class, we have a quadrophony, and we very easily, in 2 minutes, create something polyphonic with the 4 loudspeakers. This goes much more quickly than what we did in the past, and I think it will change the way people will practice these environments. The multi-channel in general, and both in Max and Pure Data. And we were very attached to the idea to provide the quality of rendering of Faust in these environments, with easyability, making it easy to use in multi-channel mode.
I can go on an ambisonic context to show how it's simple to move from one context to another. So I can add here, if I want to spatialize all those partial of the additive synthesizer, not with the show panel, but with ambisonic, we can use the HOA dot encoder at the order, for example, 3. So I will just spatialize 4 sources. So up, I will change here the number of partial. Here the number of envelope, random envelope. I need to send those messages. Okay, and we can already see the what is going on, the circular harmonic. Here we have a little utility to print the harmonic, the circular harmonic. And we have 4 sources. The encoder, the initial state of the encoder, take the circle of speaker and project each sources. It take the number of sources and divide the circle by the number of sources and project all the sources on the circle. And here we have the first source on the front of the audience. And if I modify here the angle of the first sources, we will see that the lobe in the top of the screen turning on the left. Okay, and I can add here a decoder, for example. If I have 16 speaker, I just need to write this, but here we have just 2 speakers, so we can just use a stereo decoder here at the order 3, and we need to plug that and listen the result. And I can add my reverb if I want, but not very interesting. And the particularity of our ambisonic toolbox is the use of processing inside the ambisonic domain, like decorrelation, for example. Oops. Which, if you want to just see if you want to comment a little bit of the variable.
Yes, the decorrelation, for instance, at order 3 adds 7 delay lines in the process, one by harmonic, circular harmonic, as we are at order 3, at ambisonic order 3. So we have 7 layers, and it implements 7 delay lines that and the individual duration of delay for each delay is computed according to a distribution function. And we have implemented the 22 easing functions. These are functions that go from 0, 1 to 0, 1. And the first one is most simple, the linear function from 0 to 1 direct. This is 1 by default. And Paul shows maybe I can't see if you have changed the function,
no,
the easing function, but
will.
You can change it. And the amount you see, 48,000, is the maximum delay. In fact, the maximum delay that will be achieved at maximum circular harmonic, and all delays are computed between 0 and this maximum according to the easing function. We also have a feedback and a factor of which is a macroscopic control that enables to open or close the I simplify it, open or close the decorrelation very simply with one parameter.
We have also a special graphic user interface for the decorrelation, which allows the user to control the gain of each ambisonic harmonic and the delay applied to those harmonic. And the function of distribution of the treatments is just here a way to spread the process between the harmonics. As you can see.
This is what, in fact, it's part of Paul's research during his PhD, and we added the interfaces that Paul developed during his PhD to the distribution, to the Max package. So you will find all the objects, Faust codes, and these interfaces as well in the package.
Yes.
I think now we should have some minutes for 3 or 5 minutes for questions. So don't hesitate, and if you have questions, of course. Jan has a question.
Thank you. That's is it working? Yes, super convincing. I was wondering if the decoders and the encoders can work on the web. Have you tried, or is it too heavy, or? Huh?
They should work, but I didn't try. I tried it on the ID with binaural listening, and it worked
And it was
well.
correct.
Yes.
Okay, that's nice. Thank you.
Any question?
could you just re-explain to me the function between 0 and 1, this part? I didn't understand.
Here, the factor?
Yes, like the last...
Here. It's just a number of, we have 21 function of distribution of the processes between the harmonics. And the first function type is linear distribution, as you can see here. The first type of distribution is linear. Then what? The first function type is linear, and then you. Okay. So it's 21 type of distribution. One is cosinus, square. And so. Yes. Exactly. It's how those functions are used to assign the amount of treatment for each harmonic. The harmonic H0 have more treatment than the 7/7, the 7-7, and how I distribute those amount is with those functions.
And when we experimented with the students, our students are composers, and by changing sound around the people, around the audience, it's very convincing because just without changing the maximum delay and without changing the factor, they find a new distribution, a new timbre even, because of the, if we are at, for instance, at order, and at ambisonic order, I don't know, 4, 5, etc., the effect on the timbre, the spatial timbre, will be immediate.
Yes, if the delay window of the decoration is very short, like 10 milliseconds, the effect of changing the function type, the function of distribution, will affect the filtering of the signal. And if you have a very large window, like 2 seconds or 3 seconds, the function type will affect the rhythm of the echo. And it's very interesting as a composer to have this this tool. Yeah.
Other questions? Don't hesitate. Yeah.
So you were saying that that was changing for the students. Can you explain a little bit what changes you can observe?
Yes, I think there are two big changes. The first is the time of the creation of the patch, because here, if I want to make the same thing with the old way, I need to type to make thing like that. And then connect each thing with the second object, and I need to make many connection. And if I change here the number, I need to reconnect all the objects. So the time of the creation of the patch, and and the documentation help the student to know what to do with those abstraction, and the advantage of the auto-completion helps them too.
And what I can add as well is before, when we started using, for instance, a granulator, we just implemented one granulator in mono or maximum two in stereo. And we will add the granulator, etc., connect, set the loudness, etc., etc. And at the end of the session, okay, we have something maximum in stereo. Here you want 16 granulators. Let's try a strange or totally full, amazing polyphony with 16 granulators. We don't know how it sounds, but we can try. And very clearly, we can try this very easily, very quickly, thanks to multi-channel. And with libraries like this one, we can connect it to spatialization very quickly. So there's, because in the past we had to we do it in stereo, and now we are going to move to I don't know, the quadrophony, and so add two encoders for the two sources, and then one decoder, and connect everything connection by connection, etc., etc. And you have seen with what Paul has done, he connected directly a multi-encoder, a decoder, and it's immediate. Thank you very much.
Oh. So next speaker is Léon Gnedider, or obsolescence. How do you spell it? He's going to show us how he's using Faust in the context of the Rust language. So it's more of description of your personal experience and as a tutorial or something like that. You are from Germany, or? Yes, okay. The nice thing is that, so we have the Rust backend in Faust since 2017, so it's already a bit old, but we have few people using it, and now we have more and more people starting to use the Rust as a a safer language to do low-level processing and efficient code like you would do in C++, but plus the safety that you can obtain with Rust. And the Rust audio community is developing quite fast now, and having this kind of force for Rust path is a way for us to reach this community in some way.
Okay. Nice. I will talk today about my experiences with Faust and Rust and how I'm integrating those two languages together. First, a couple of words about me. My name is Obsolescence. I'm mainly something between a techno DJ and a tinkerer. So I like doing a lot of different stuff. I like working with electronics. I love working with programming, with design also. And yeah, so I'm doing a lot of stuff, which means I don't know anything of that really well. And yeah. So also because I'm making music and building the things at the same time, maybe some of you also know this difficult decision sometimes. Okay, first a couple of words about projects that I'm working on. Equi, that is the main project that I've been working on a long time. It's the reason why I got involved with Faust and Rust at first. It's a DJ Mixer as a software. I was really annoyed by the solutions that are out there, very expensive, very difficult to carry. And I thought, why not just make a mixer as software? And that's where my journey with Faust first started, and then later with Rust. It's a lot about filters. It's inspired by Allen and Heath and the Model 1 mixer, in case you know them. If you're into mixers or DJing, go check it out. Let's see if we have this big enough or small enough. Yeah, that looks right. Okay. So just to give you an idea about the user interface, nothing crazy, just some faders and colors. Just the routing possibilities. It's a Jack application. I like to do my stuff with Jack. It allows to have external effects, to route them back in and stuff like that. That's my setup. Here you can also see the hardware that I'm building. And another piece of software that I'm working on is called LipoCDJ. It's basically the vinyl player of this part. So it's like modularized or like the CDJ kind of thing. It's also written in Rust, but not using Faust because it's mainly working on samples, on MP3s and stuff like that. And my idea with the software is to build something that is reliable, good sounding, and can actually be used in clubs and festivals. So is kind of on a professional grade. Of course, also fun to use. Yeah, the problem with a lot of DJ solutions out there is that they're very proprietary. Everything is locked down, cloud stuff and shit. And to me, that's very sad to see, because in the end, we're just playing music of other people. That's nothing crazy, but still the whole market is getting locked up. And yeah, so I got encouraged to write my own stuff. And yeah, that's the design part. Not there yet. I'm currently writing a new GUI for it. For making this possible, especially Equi, I very early got involved into a project that funnily a friend of me started. It's called Rust-Faust or Faust Build and Faust Types. It's a kind of ecosystem in the Rust world. And I will talk more about this later. And last year, Magnetophone, maybe you know him, he's building compressors and stuff. He asked me to help him integrate the Rust Faust stuff into NePlug. NePlug is a Rust crate or library that allows, it gives you a little bit like the Juice functionality of writing one code base that you then can export into different plugins, LV2, Clap, and so on and so on and so on. So I wrote this template project to easily get you started and help you out with integrating those two worlds. If anything of that sounds interesting, we're looking for friends, hackers, designers, people that want to get involved and
join our journey on this. You can find us on Goldberg or GitHub, or you can send me an email. Here a couple of links. I thought, why not start a talk about Rust with why you should not use Rust? And it's very much hyped, the whole language, and I want to give you a little introspection on maybe why not Rust. And the main thing for that is the learning curve. It's not one learning curve, it's multiple learning curves. I tried to track down a little bit how my learning curve felt. It was a lot of ups and downs, ups and downs. And you also see this a lot in the internet. But I also don't want to discourage you of starting learning Rust, because this is just the learning curve or the difficulty curve. There's also a joy curve. And that pretty much looks like this. Overall, it's a very joyful programming language. Of course, has its ups and downs. Sometimes you go back to other programming languages and then Rust feels even more joyful again, because you really get a lot of nice things with Rust. But there's also discontinuity in this curve. There's some parts that are really annoying in Rust also, but it's mainly about async, which we here rarely, I think, touch. So for audio stuff, low-level stuff like that, really check out Rust. It's really nice. I wrote down a couple of things, just like a mind map or something of things that I think are really nice with Rust. We have Lisp-like macros that are really working on the AST level. It's, in my opinion, a very beautiful syntax. We have no garbage collector. We have a very novel new idea of how to do memory management. We have an algebraic type system, which allows us to really safely model a lot of things and write really beautiful code. We have a package manager, a lot of really cool stuff. Go check it out. Often Rust is referred as an alternative or improvement over C or C++. I disagree on that. I think it's a new thing. It's a new way of programming. And same as I also think Faust is a new way of programming, maybe now already 10 or 20 years old. But I think it's a different and new way of programming. And this is also the reason why I think, okay, I think why Faust, we all know that. Faust is amazing. I think all those things are reason why I think combining Faust and Rust is a very interesting thing to do. We have both our progressive languages have some functional stuff sprinkled on top of it or are that. Both things run at a lot of different places. We can do all platforms, Arduino, embedded, CLAP, LV2, and so on and so on. And combining those two things also allows us to combine both ecosystems. With Rust, we can do GUI. With Rust, we can do audio host stuff, a lot of stuff. For this workshop, I thought about let's build something together. I will not live code, but I will walk you through all the different parts of this. The application that we're going to build is something like this, nothing crazy. We have a stereo input, stereo output. We have a volume control. We have something that makes a RMS, so shows us the current volume. And we have also a peak meter that we can reset with this reset button. Nothing crazy, but I think it will show us how to do the architecture of the application, how to send state parameters from the user interface back to the backend. Here this picture is, of course, only the Faust IDE stuff, but we will take that DSP and integrate it, embed it into Rust, and write the GUI in Rust also. And use Jack to do the audio host stuff. Talking about the dependencies, the Rust Faust ecosystem we will use, Jack, as I just said, eGUI, it's my decision for the GUI library. It's an immediate mode GUI library completely written in Rust. So this all allows us to have very little C, C++ bindings, and most of the stuff is written in Rust.
You can also find the template on my Codeberg. It's like 9 commits that implement all the different parts. So you can check it out and follow the different parts there also. Here in this presentation, I will only show you like some snippets of the different code parts that I think are most interesting. So for the full examples, go check out that template. First, I want to talk about the project structure. I like to, or like with Rust, we have a really nice feature. It's called workspaces. It allows us to split our project into different sub-projects or different crates, as it's called in Rust. So we have, for example, one little library that is the DSP and just a little layer on top of it to make it convenient to use. Then we have the backend that integrates with the check server in this case, but it could also integrate with something else. And of course, we have the GUI. So it's split into those 3 modules. First, we will start with the DSP. And for this, we of course first have to have some dependencies. And with Rust, this is as easy as running this command. It will automatically download the latest version of the Faust build crate, so the Faust build library or tool, and the Faust types. Those you can find here at this GitHub. Yeah. Next thing we can do is we add some Faust code. I added here the code that I'm using for this. I will not go into details about that, but just so that you have seen it. Why is that not working? Okay, whatever. Okay. So we take that code that we had here. I don't know. That's not really working. The code that we had here, and we added into crates, DSP, DSP main DSP. That's where we lay our Faust code. And to build this code, or like to compile the Faust code into Rust, there's this tool called Faust Build. It's Rust code. It's a Rust library that we run at build time. So it's basically a pre-build script that's running in Rust. And to start using that, it's as easy as creating the build.rs file under crates DSP with something like, wait, that's out of sync here. Yeah, here we see it. So it's basically saying, hey, take the Faust code from DSP main DSP, export it to, what is this here? Why is it not working? Is it working like that? Nothing is working. Let's try out something. Now it's working. Oh, better. Okay. We have to work with what we have here. And it also gives us a couple of options. We can do different things here. For now, I'm only defining the struct name that this thing will later on use. But you could also define, like, I don't know, use doubles, change the module name. Basically, all the CLI flags that you have with the Faust minus lang Rust stuff, you can define here. So Faust minus build is basically a wrapper around the CLI tool. It invokes the CLI tool and gives us a convenient Rust wrapper around that. And yeah, what we're also doing here is this part should only run if we are building this DSP crate with the Faust rebuild feature. It's the way how I do it, because I don't want Faust to rebuild it every time I'm building that stuff, but only when I want it to make compile times shorter. Also, you also don't have to have the transpiled or compiled Rust code laying in your repository or like in your project. You can also have it in like the target temp folder, but I really like having the generated code next to my stuff. That means other people that run my code don't need the Faust toolchain installed. And I think it's just convenient to have it there also for version management in case stuff breaks. What? I will try restarting this thing. This is super annoying. For the feature to work, we also need to define it in the cargo toml file, but yeah, that's easy to do. So this is the full command that we will run to generate the first time our Rust compiled code. It's as easy as invoking cargo. -p says we want to build only the DSP crate in our workspace, and we enable the Faust rebuild feature for this one. Next, wrapping the Faust generated code. It's nice, it's fast, a lot of things are good about that, but it's not Rust idiomatic code. And that's not really a problem because we can just make this ourselves around it, and maybe it's anyways useful, needed for your specific project, because you will probably have different needs and likings of how you want to interact with your DSP code. So I think it's anyways a good thing to do. And but at the same time, there's also people currently working on trying to fix that stuff, especially Crop 2000. He popped up the last months, I think, or at least that's when I got to know about him. And there's a couple of issues and PRs around. So in case you're interested in that, check that out and join the discussion on that. Yeah, so for the wrapping, it's as easy as we define a struct. We call it Faust or like DSP, and it basically holds or has a field with the Faust DSP. It's the stuff that is generated from the Faust compiler. And on top of that, we implement our own API. That's happening in this impl block down there. Here. So let's start with something very simple. Just setting and getting the sample rate. Wait, no, first the new, that's the convention, that's basically the constructor in Rustland. We return ourselves and we just stuff in the Faust DSP here. Then one problem with the generated Faust code is it's using very often E32s, 32, so integer 32 bits at many places. I never saw a negative sample rate. I don't know if that's possible in some theory land, but I prefer my sample rates to be a U size and unsigned number that is aligned with the array and vector sizes that we're using. And so I'm simply wrapping that. I'm simply taking in a U size, I convert it into an E32 so that Faust DSP is happy. And to get it, we do the same thing the other way around. Also, the convention in Rust is for setters, you prefix it with set, but for getters, you leave it away. Just a convention thingy. Easy peasy. Next thing, parameters. In Faust Rustland, we need to have param indexes everywhere. So this is a snippet of the generated Rust code. We basically see here, maybe you saw it already, we have a button declared for resetting, we have a volume slider. What else do we have? And we have, of course, the UI parameters like the RMS and the peak indicators. And I personally don't want to use indexes. I also don't want to have strings that are somehow flying around. In Rust, we try to really nail that down. and we do that with enums. So we have the volume parameter that we can set from the UI, and we have the reset button, of course. And we define this enum, and we implement a conversion from that into param index, which is the type that the Faust generated Rust code expects. It's as easy as matching against that and just doing that stuff here. For now, this is hard coded. If you have a bigger project, you should look into alternatives to do that. I wrote a macro for this. You can check out Equi and Neplug. I also wrote something like that. For simplicity, we will just hard code it here. But we also have UI parameters in Faust. It's possible to set UI parameters also. I think I saw that in the code. I want the UI parameters to only be gettable but not settable. And this is the reason why I have a separate enum called UI parameters. It's basically just gettable parameters. Same story here. We just map them to the param index. Now that we have those types and enums laid out, we can extend our DSP implementation. Where's my mouse? Here. And the code for that is quite easy. We have a set parameter function. It takes the parameter. It also takes a value of a float, 32. And then we call the internal Faust DSP set param. We convert it with just a simple into, and we set the value. Easy peasy. And to get it, we just do it the other way around. And for the UI parameter, we only have the getter. Yeah. Here, this expect is in case something goes wrong, that we have a nice assertion or panic message. That was the easy part. Now we come to Faust Compute. And Faust Compute, maybe you saw it already. It's basically the function that is actually running the DSP and computes all the samples. And the problem is Rust Faust expects here a slice of F32, which in theory sounds good, but in practice it's a bit annoying. One reason it's annoying is the amount of inputs or output channels. It's constant, it's not changing, but it's not encoded into, or like, encoded into the API. So we can throw in as many or as little input or output channels, and things can get a bit nasty when we are converting our vector of vectors or our 2D arrays into this kind of structure. So what I like to do is wrap this in a little bit nicer API, and I will show you how I do that. And of course the count type is again an E32 instead of a usize. What I'm doing is I basically hard code the input and output channels inside this type as a constant. And this allows us to use this type also outside to allocate those buffers later. And this way just make sure that all of those things are in sync. And those variables that we define here, those constants, we will also use in the compute function. You will see later on. So here, this is the API for our compute function. We take the count as a usize. We take a slice of E with the length of inputs. We have a mutable slice for the outputs. It again has the length of self-outputs. Now you might be wondering about this E and O parameters here. What we're doing here is we abstract a little bit away what is below that to make it compatible with both an array and a vector. And it basically says for the input, we need something that is as ref of an F32 array or slice. And for the output, we need this to be mutable so that we can write into it. And the code for this looks a little bit like this. We need to change the memory layout a little bit so that we have the slice of slice things that the Rust Faust stuff wants. So basically we write this, we take the inputs as ref. Here we need to write something with an iter to make this in a safe code so that we don't have to use unsafe. It's a little bit not nice. It's a little bit hacky to write this stuff, but at the same time, you write this runs and then you have it. And once we generated those types or like those this memory layout, we can then stuff it into the Faust DSP compute method. Nice. So another thing that I'd like to do, but this may be different for you, different for the needs that you have. I like to create one struct container for the state that I'm having that I want to send to the UI later on. And basically here I'm laying out the RMS peak, the volume parameter and the reset parameter, all F32s. And I implement an update method on it where we can stuff in here the DSP instance and just pull out all the parameters and values for those things. Just a little convenience thingy. And then on the DSP, we can just have a little function that does this all for us. So now the interesting part is how to use all that stuff now. Basically, the DSP part is now done. And the way I'm using it is like this. Creating a new DSP instance, simple as that, DSP new, sample rate, also very straightforward. Now it's getting interesting how we allocate the input and output buffers as array. That's this here. So we create a 2D array where the outer length is DSP inputs. We could also write inputs as a constant here, both works. And here we set the max buffer size, so those are not resizable for now, but that's fine. And similar stuff for the outputs. We of course need them to be mutable for now. And then we can call the compute function like this. Normally I use vectors, like a 2D vector for this kind of stuff, because maybe the buffer sizes changes or other things changes. So I want to be able to grow or smaller them on doing runtime. And this we can also do. We can do a vec of vec. The syntax looks very similar. Here we also use the constant, the inputs and outputs constant. So this is always in sync with our DSP, which I think is quite nice. And for throwing them into the compute function, we need to write a little bit different code for this. We need to do this little thingy here and that. It's still a bit annoying, but I think it's still quite ergonomic to use and nice. For the parameters, we will now have this function, this API here. So we just invoke the enum of the volume. We can set a value. Same for the reset. UI parameters, same story. To create a default state, we can just use the default function and then call update state on that. Nice. Is anyone programming in C here? Okay, that's quite many. Anybody wants to play a little game? Nobody? Okay, then we can play it all together. Which functions of those are in the C standard library, or is it Welsh words? Welsh is a language. I had to Google all of them. I didn't know any of them. Anybody here in the room who knows exactly which are the 4 Welsh words? Okay, nice. You want to say what's your opinion, or what do you think is the Welsh words?
Welsh words are
Okay, let's see. I think you were correct. Nice. Really good. Okay, let's continue with the backend. What's the task of the backend? I want my backend to initiate the jack audio client. I want it to fire up the DSP stuff. I want it to create the real-time thread and all that stuff. And it also gives us a convenient way to send parameters from the UI to that in a real-time safe way, and also send the state back to the UI thread. Also, of course, in a real-time safe way. For sending the parameters to the backend or to the audio thread, we will use a ring buffer. And to sync the state back to the UI, I will use a triple buffer. And how I do that, I will show you. First, we will add a couple of dependencies. Jack, RTRB is the ring buffer, triple buffer is the triple buffer. So the struct for Jack backend looks something like this. The DSP, that's the wrapper that we just wrote. Jack client, it's holding the Jack stuff. Ports in, out, that also Jack stuff. We can ignore that for now. State writer, it's where the Jack thread can write the state into, and we can pull it out on the other side in the UI thread. Comment consumer, it's where the Jack thread can read out the comments that we send to it. Those types, the comment consumer and the state writer and the types for the other side, we will define ourselves. It's basically, we alias those types. So we create a new type. It's basically just an alias for that. So state reader, state writer. We just take the output type. We stuff in our DSP state. Same for input. Stuff in our DSP state that we defined in the DSP crate. Comment, we define as a tuple of a parameter and an F32. Depending on your application, you maybe want to have a different layout. For Equi, for example, I have different types for my different parameters. Some of them, I only want them to be Boolean, stuff like that. So you can lay that out how you want it. And producer, consumer, same thing again. So this is how we create the Jack backend. We first instantiate the DSP. Then we instantiate the Jack client. We register the parts. We can skip that. For the triple buffer, we create a new one. We stuff in default DSP state, and we split it into the state writer, state reader. Similar thing we do with the ring buffer. Here I give it 24 slots. I get a producer, I get a consumer. And this new function returns a tuple of three things. First, the Jack backend instance, and then the state reader and the common producer. State reader is what we give later on to the UI, same with the common producer. The run method in the Jack backend, it's what will actually start the Jack client and have the loop, basically, that is running the DSP compute, that is also retrieving the comments from the UI and also sends and syncs back the state. Here we have also some stuff to gracefully shut down that thingy. I will skip that for now. If you want to look at it, check out the repo. We get the sample rate. We tell the DSP what the sample rate is. Then we initiate or allocate our input and output buffers, same as I showed you in the example before. Just for a good measure, I will double the Jack buffer size that Jack tells us it wants to have. I also have a variable last UI state update. It's basically a timestamp when I last synced the state to the UI, because of course the DSP is running at a much higher rate at the UI. Normally the UI we have 60 frames per second. the DSP probably is hopefully running a lot more often per second. This here is the function that is getting run by Jack. So that's basically our real-time or like our real-time thread here. Oh yeah, the audio callback. A couple of things here and there. We get the length of the buffer that Jack wants. We check if that fits to our buffer. In case of not, in case it's bigger, we grow it here. In case of the sample rate changing, which can happen with Jack, we of course update that. Then I like to copy the audio input from Jack to my own buffers. Probably there's a way to use the Jack buffers with Faust directly, but I like to do it this way. And here, that's interesting stuff where we retrieve all the comments from the UI. It's basically a while loop where we pop it until we popped all of them, and then we stuff it into the parameter and into the DSP. And we also say the state changed, so as soon as the new parameter came in, we sync a new state to the UI. Something that I learned from Stefan, I think that was our first interaction, was I had a problem with my filters just doing weird stuff at some point. And Stefan was like, did you flush the denormals? And I was like, flushing what? Still don't really know what it's doing exactly, but in Rust, we have a quite well working library, in my opinion, that is just giving us this really convenient API. We call it, this is the syntax for an anonymous function or like a closure or Lambda or whatever you might call it. And everything we run inside this Lambda, it's with the flush denormals. So here we then actually compute the DSP. And same thing as I did in the example before. Now we only have to copy out the audio back to the Jack buffer. And to sync the state back to the UI, we check if the state changed flag is set to true, or the last update is longer than max elapsed UI write. And this is how we use the triple buffer. So we get a writable input buffer. We call the DSP update state method on that buffer. We say it should publish it. And of course, we set the timestamp to what we have right now. That's it. That's just stuff for Jack. We will skip that for now. I also like to have next to the Jack backend specific stuff, more general backend module or like struct. So in case I'm having multiple backends, I could have a generic API on top of that here. What is interesting here, maybe? If you look at the layout here, it's holding the comment producer, also the join handle for the graceful shutdown, but it's not holding the state reader. We do that because for the state reader, I want to get a reference to it, a mutable reference, or like it's borrowing it as mutable so that we can read the state. And in Rust land, that would mean the whole object is borrowed mutably, and then we cannot borrow another part as readable. Something that when you start learning Rust, you will fall on this thingy many times. It's one of the learning curve hills of learning how to deal with the borrow checker. And very often, if you have this problem, especially if you want to borrow multiple fields of one struct as mutable and non-mutable, think about if you can split that struct into multiple parts. And that's basically what we're doing here. And I think the most important thing about this is basically we just wrap that. We, by default, handle the error of the ring buffer being full here. Error, exclamation mark, it's a macro that is doing error logging. Check out tracing, the tracing library for error logging. No need to hand roll that yourself. And implement drop for backend. It's basically the deconstructor, like this RAII stuff that you also have in C++. So when the backend is getting out of scope and is getting destroyed, we also turn down the check backend logic to check for it. Check in, are you still with me? Everyone's still around? Ah, okay. I think Rust is a little bit like when you talk with people about Linux or NixOS or stuff like that. People can easily get annoyed. So in case you're annoyed, feel free to get to the coffee break. I would still talk a little bit about the GUI side. It's very quick though. Okay, for the GUI, I already said we use eGUI, or I use eGUI. We again have a constructor for the app. The app holds the backend and the state reader. And we construct those two things. And then in the app, we basically have the render loop, the function that is called on each frame, and it then lays out the widgets and draws all that stuff on the screen. And in the beginning of that, we get the freshest state that we can get out of the triple buffer. That's what we do here. And then we can just on state call .volume, .rms and stuff like that and retrieve those things. Here, the CQO central panel, it's just like layout stuff. We do heading, yada, yada, yada. Then we add a slider. This is just the eGUI syntax to, whenever we set a value, send it back to the to the backend like this, and otherwise give back what the state currently has in. A little bit of an ego thing. You can have a look at it more clearly if you don't understand it yet, or ask me later about it. Similar thing for the RMS. I just put it into label. We just pull it out of the state, format it a little bit, create a label. And then we, of course, have the peak label that's showing the current peak. And next to it, a button where we can reset this peak thingy. And we just check, basically, if the mouse is pressed down on it, we send the command reset with a 1.0. And when we release the click, we send the 0.0. Here, you, of course, could also think about just sending a true or false if you do a little bit different parameter wrapping. Yeah. I would skip that. It's just a little boilerplate to get it started. And what we will end up is something like this. An application with the slider, with the label, with the peak, and with a reset button. Not really beautiful, but I think it already shows how to architect an application like that. And I think, or hope, that this can be helpful for a couple of different projects that you want to do with Rust and Faust. And hope you learned something. A couple of recommendations in the Rust ecosystem. Neplug, I already talked about it. It's like this juice-like thingy where you can export multiple different plugins from one code base. Vizia, it's a GUI framework specifically made for audio plugins. Slint, it's basically QML or Qt-like audio development in Rustland. Symphonia, in case you ever need to read MP3 FLAC or anything, it's they build like encoders and decoders for all those formats in Rust. I use it in my DJ program, works really well. That's it. thank you for listening. Shall we still do questions or coffee break? Okay, perfect.
Okay, so before we start the new session, I have an important announcement to make. Jan actually made a reservation tonight at a pizza place for 20 people because he thought that
and then we can possibly discuss something if you think you have something to say. So basically what we call tools and ecosystem is everything which is outside of the Faust language and compiler itself. So I'm going to complete what I've explained and showed in this morning session. What is missing? What is missing in the sense that we cannot do everything at GRAM and in the MEVO team, and that we need the help of the community. How can we organize this in a better way? Yeah, this is basically what I want to show. What is new is that we, as I explained this morning, we had the creation of the MEVO team. So in some sense, there is less workforce at GRAM. I'm now the old guy of the team of before when Jan was working at GRAM. Jan moved to INRIA. He's obviously working for the MEVO team and working on the Faust compiler. As you will see just after this roundtable, we have a lot of new things to show, to demonstrate. So it means we have somewhat less workforce at GRAM, working directly on the Faust compiler and ecosystem in general. The other thing is that part of what is done on the Faust language and compiler is driven by needs, technical needs, research needs that we have in the MEVO team, and especially project, the FAST project, which is about developing engineering stuff for FPGA based audio boards, and all this work on the Cifala toolchain. So it means we have to deal with this specific connection with the MEVO team. The interesting thing that happened the last 2 years is that we have less workforce internally, but we were able to have a very interesting Google Summer of Code projects. In 23, we had 2 Google Summer of Code. The first one was taken by Tommy, who did this automatic differentiation work. At that time, The idea was directly to add automatic differentiation inside the compiler itself. So this was the first manner to work on the question. It's still possibly something that we will do at some point. But yes, it was initial work on having automatic differentiation in the Faust compiler. Again, our vision is that since we are designing a domain-specific language, and since we are more or less controlling everything from the language to the compiler, we think that having auto-differentiation as a first-class concept into the compiler is probably a way to explore, and then obviously automatic differentiation, then all kind of machine learning projects that you can imagine. Then this idea of having this into the language and the compiler, we think it's something original to explore in some sense. And now we have Benjamin working also on this subject as a PhD, a CIFRE PhD that we have in France. And the second Google Summer of Code was this work done by Jan Klester, very bright student, PhD student in Georgia Tech, I think. He did all this stuff, improving the Faust web stack that we have, the Faust WASM project, and all this development, the Faust web component. And this year it was even better because we had 4 projects. So it means 4 mentors, or at least 4 mentors, or maybe 8 mentors to help for the project. And we had those 4 subject to project to follow. First one was the idea of having a VST clap plugin embedding the Faust compiler so that you can program in a dynamic way. So basically, you can code directly in Faust in a VST plugin and have the code compiled on the fly using always the same technology, libfaust, LLVM, this kind of thing, or the interpreter backend. The project is not finished, but it was move on from the state before. There was already an Amati project before the start of the project, and Amati++ is the evolution of this project. So we have some things that we can continue to build on. The second one was the idea to add Faust as a language to be used for audio processing into the cable.gl framework, which is a pure web framework for graphic and audio and control stuff. That it's a pure web application. And there was a project to embed Faust, in this case using pure web technology. So again, the libfaust, the dynamic compiler, so that you can, as a user, you can program in Faust and have the code be compiled on the fly and be running as a web audio node. FaustNet is an evolution of the initial work of Tommy, basically working on extending the DDSP Faust library that has been developed initially by Tommy. And so the idea was to complete the library and explore neural network coded using the differentiable library, so the autodiff library. And the last one is also an interesting subject we want to merge at some point. The idea is to have a real packaging system to be able to connect with Faust libraries that are developed at other places that the standard place that we have in Gram. So we had a student, an Egyptian student working on this. And up to now, we were not able to merge the result of the project, but we plan to do it quite soon. So basically, we will have a kind of official way to plug external library, deal with versioning issue, this kind of thing. So this is a way to have more workforce in the Faust ecosystem. As I explained this morning, we have this new backend, the new Faust, some new Faust XX, Faust 2 something tools, and part of my work is fixing bugs. Yes, you don't see it, but well, it takes time. And trying to keep the ecosystem as generic as possible and as not to make a specific use case, and try to keep the overall idea. And in concretely, it means that I'm maintaining the three main websites that we have: the Faust, Faust Doc, and Faust Library. Merging pull request mainly on the Faust project and Faust library. We have from time to time improvements on libraries. We did not have any new library, complete library 2 last years, but continuous improvement into some of the existing libraries. So I'm also filling regularly the Powered by Faust page, which is also a way to say something is happening into the Faust community, and listing all the project is a good way also to keep an eye on all these things. And we started basically last year, I think, using a Discord channel. So moving from Slack, which is a platform that you have to pay for if you want to keep the older messages. So we moved to Discord. So now we have people, most people, the real-time discussions we have in the Faust community happen on what is missing. So there are always things missing. We have people complaining. There is not enough debugging tool in the compiler. Yes, we know that. It's not easy to do. We have a bad error message in the compiler. Yes, we know that. What I've done in the last 2 years is at least try to document the existing error message and classify them by category, like syntax error, connection kind of error, semantic error, so that at least as a user, you have a more deeper understanding of what part of the compiler display a specific error message, which at least help a bit, and trying to change some of them, means the message itself. We would need probably to improve all the signal analysis stuff that we have into the Faust IDE. But Faust IDE is an external project that was developed by a very bright Chinese student, and it's also difficult for us to maintain this project. So maintain is okay, but adding new stuff is always difficult. We try to, we have GitHub issues that are coming on a different project, and I'm obviously not able to follow everything and fix everything. And I wrote this just after the workshop of Alain and Paul. Yes, we have external development done by, for example, Albert Greff, this Faust Gen 2 external that allows you to use libfaust, so the dynamic compilation chain in pure data. So the community would need to update it to a more recent version, but Albert is I think he's a bit lazy now. He doesn't want to fix it. How can we do that? I don't know. Your idea. So maybe now how to engage the community. So how to engage the community is we will try to give some answer at the last roundtable tomorrow with Jan. So we have an idea of creating a Faust consortium, and AFA means association, Faust association, sorry. It's for French and English way of saying Faust association. So obviously a creation, the name is a creation of Jan. Only Jan can create this kind of acronym, I guess. We will speak about this tomorrow, and it's a way, the Faust association, it's possibly a way to gather interested people. Yeah, so now maybe we have some minutes to, if you have some comments, to say some advices to give us. So we are a very small community, but we try to be active. I think with the MEVO team, we have more workforce, but probably more on the research part. I mean, we are not, we don't have people working on the ecosystem itself, apart me, on the Faust Emerald, because we are an academic team, so we are supposed to produce results and papers and white papers and this kind of thing. So it means obviously it's a bit different compared to what was the situation before, when all of us were at Gram, when we could do more or less the way we wanted. So the situation has changed a bit. But for Jan, it was also more focused on Faust. So I think he has very impressive result to demonstrate just after. I mean, at the language level, with different new feature in the language, which was something done in the last 2 years. So what can I say more?
Maybe one idea to engage more people would be to make a MOOC, massive online free course, because now there is the course on Cadenza that is very good. I learned there, it's fun, but not all the people want to register on Cadenza, to pay for Cadenza, even if it's not so much. So, for example, like the people of Pharo have this online course, is there to get more people.
Yeah. It's a bit of work.
Well, on Cadenza, you don't have to pay anything. Like you only have to pay if you want to want a certificate. But I think it's a very good point. The thing is, it takes a lot of time. And so I mean, when Jan and I did the Cadenza course, that was like what, 5-6 years ago or something like this. So it took us like a solid month of work, full time, just to put it together. And it's true that we should probably make a new one and a little bit more updated. But like, I mean, if someone in the community and who's like still like doing a PhD or whatever, like wants to do something like this, that would be really great. But like the thing is, I think that Stefan, me, or Jan, like, I mean, finding 1 month in our schedule to do something like this full time, it's basically impossible, you know. And so maybe it could be like something that multiple people do together, but like students or whatever. But it would be very nice to have it for sure. But yeah, like, I mean, finding the workforce to do things like this is pretty tough. And also, like, finding the right people to do it is also not necessarily that simple, because in the end there are not that many people like who can do things like I don't know. Yeah.
So maybe we can not do a full course again, but maybe some more regular. I don't know what do you expect? Would you like to see? Okay, a MOOC. Okay, maybe it's out of the scope right now, but we can maybe more regularly produce some content, and this can be also the role of the AFA association to do that. So it's an open question. We want ideas from you and needs. And
we were just discussing today with Jan. What we can do quite easily is do regular video meeting like they do with the audio programmer community. The guy invites some people presenting their project, and we could possibly organize under the AFA association some regular meeting, just asking the community, Michel, do you want to demonstrate something new into one things? And we have a lot of projects that are emerging.
Yeah, that's a bit the idea, making 7 minutes videos about one topic, like live coding.
Yeah,
and there is one guy called Daniel Schiffman that is producing videos every week, you know, about steering behaviors, AI, creative programming, making a tuner for ukulele, and things like this. It's really like that. And this last example depressed me. Put me really depressed. Yes, yeah. I tell you why later. But yeah, I spent many times working a guitar tuner, and this thing in processing in 5 lines of code was better than mine, thanks to a machine learning model that really killed my heart, because it worked better. Okay, so yeah, this guy is making very lively videos, but he make mistakes in front of you, and he fix them, and so on and so on. It's really not so much prepared, but it's live, and it's about different topics. So you could engage the community, or even yourself, try to do things like this. Maybe it's not like a MOOC where you've got to rehearse and prepare things and so on.
Yeah, it's a way to be lighter.
There's one thing that we talked about many times before, which is that so right now we have somewhat reasonable documentation for the syntax of the language, you know, and there's the Cadenza course and a couple of other resources that basically show people how to start from a known DSP program and then just write it in Faust. One thing that's potentially missing, and this is something that we talked about, but it's very hard to sort of describe it, is Faust writing idioms in a way, you know, like so meaning that how do you actually write Faust code, you know, like and not just from a semantical standpoint, you know, like but like if you want to do this, how do you write it, you know? And to me, that's something that's really missing right now in the documentation, because very often people who use Faust and who already have a programming background, they tend to think in a slightly different way than the way Faust works, because Faust is functional, and people tend to think more in a very imperative way. And so then you try to write something in an imperative way, and then it doesn't work, and then you're like, how do I actually write this, you know? And so this is really something I think that's missing in the documentation. And I think if we had to make videos,
to be,
this should be like a priority for.
I have
for
a
sure.
list. One of my plans for IFC was at some point to do this kind of thing. So I've started like 3 years ago putting different things, and the idea was to put a list of Faust idiomatic ways of writing, and also trying to extract good ideas that came from the community. Because if you look at the Faust library, then you can see emerging higher level way to think about DSP stuff, and those have to be documented. And probably, yes, it's a bit of work because you have to dig into a lot of material. I have started to write something, so there is already a document that could be completed. There is also something that we know as a functional programmer is that with Faust, with the pattern match stuff, and with higher order programming, you can do very, very crazy things. So at some point, it's too complex to understand because higher order programming, first functional programming can be difficult to understand, but it's very powerful. And my feeling is that it's still underused in the Faust community because people from the functional programming way of thinking, they are not too much into our community. And we know with Jan, obviously, that we can explain people how to structure your code in a very stacked manner and create the good abstraction that you can do. And this is something that could be part of this idiomatic way of writing Faust program.
So maybe what about having the community saying, okay, proposing topics or subject, or how do you code these kind of things? And maybe that could be the opportunity to make a video or something like that. So what do you think? Would be that a good idea? Do you have a feeling that you would like to ask us about how to write something, or never occur? Yes? Okay, so maybe this is something we can do.
A simple example, Dario Sanfilippo, who is a good Faust programmer, he wrote some blog, he has a blog, and he wrote different blogs about Faust programming, and he wrote about how to deal with recursive stuff, and different ways to write recursive code. Starting from the way we did 10 years ago, which is very difficult to understand, then using a more state variables that you update at each step into the recursion, up to using the letrec approach, which is a way to rewrite your recursive code in a kind of easier way of thinking. So this is a kind of blog that is very interesting because it's a way to, extract the good way of doing this and the better way to write your code so that people can understand your code, basically. So just on the idea of having a recursive code, which is obviously important to our domain. So just thinking that we could do this kind of thing into a lot of different domains. There is also a subject on how you separate the DSP part itself from the GUI part. There are also some emerging patterns that have been done into the Faust community, but they are not documented anywhere, even not in the FAQ or a bit, but not very much. So there are some patterns that we will have to document, yes.
Maybe, yes. Oh.
Or a book written in parallel by identical people, yes. It's another more ambitious way. Maybe we can start by blogs and.
There is currently only one book written about Faust, and it's in Korean.
Yes. Yes, it could be a way. I understand, but you don't know. Yes, maybe. Oui. The simple example of.
Maybe Stefan, I can give the example for concerning programmation of composers getting initiated to programmation. And I can say teaching now in Paris 8, we have 8 times 3 hours, which makes 24 hours of introduction to Faust at a level of license 3. And people they have learned the year before, they have learned Max or Pure Data. And for them, it's far easier to make the connection between a functional language like Faust to Pure Data, the way it works, to understand the splits, the merge, etc. From the graphical
so you mean having,
understanding of a problem.
Yes, interesting. So you mean they had the Pure Data course before Faust, and it helps them to...
It helps them a lot. In the past, I've tried many formula because I try to introduce them to procedural programming, classical programming in various languages, Python or anything else. And for them, it's very, very difficult to come to classical programming, whereas it's more simple for them to go into Faust and following what they have done, for instance, in the previous semester inside patches, in fact.
But maybe you would have the other way we could work also, starting with Faust, having the split, and then how do I code the split operator of Faust in Pure Data? I'm not sure this is
and I find the interaction very productive for pedagogy.
Yes, because the initial idea of Faust came from looking at the max patch, but in the reverse way. So you explain this. So the max patch as a mathematical expression with arrows and operators, and then you move it as an expression in a language. It was the initial idea to. So obviously you have a clear connection.
And I can say that what I could do on my side, very simply, for the moment, the Moodle, which are deposits where you put everything you do every time at every course, could of course be public. For the moment, they require to be a student or a professor in Paris side, but it's very easy to configure them to be public, for instance. But in fact, it's difficult because it's a result of what we have done in class. But at least there is very simple code done by musicians. And maybe the other idea also would be to share real code that was used by creators in installations, mixed music, and to share this code that make connections between people who have created music or anything else with Faust. And
the more code we have, the more we can give to ChatGPT, and the more we can possibly get some.
Because as you said,
GPT.
As you said, I think there is a style of writing with Faust when you start making artistic projects with it, and you work with it, and you make prototypes. And it's different from pedagogical examples.
Alain, I think also all the work you did on recreating effects of historical pieces of electronic music, and this can be also a different. So how do we reproduce this equipment that was used in the Cologne studio or whatever? Could be an interesting entrée. How do you say that? Point d'entrée. Entry point for. Yeah.
So every time when I tried Faust on different platforms, on the ESP32 and on the DAISY seedboard, I had a lot of trouble to get it run with the library. So I had a lot of bugs, and so for me, I'm not sure if maybe I didn't just looked it up in a good way, but for me it would be really helpful if at least the version of the libraries would be clearly documented, that you know I need this GCC and I need this DAISY seed library and this Faust version to run together, because then I spent like days to get it working. And
And when you have it working, could you give us back the information? Because we are exactly into, I don't do it anymore. Romain, who did part of the initial work on ASP32, is not doing this anymore. And so we have lack of time to do that. Same for the DAISY. I did the initial architecture files, and it was more or less improved by someone else, but I have no time to maintain it. So we have at least, as a community, you have at least to give us back when you take days to make something working.
I will do. Yeah.
Please, at least we can put this somewhere, and for now we cannot do better. This is a lack of workforce.
Yeah, I'd just like to reinforce that point. Actually, there was an issue with the Faust Teensy tool last year, and it's really only because I'm working with the Teensy quite heavily that I was in a position to take some time to see what was wrong. It turned out there'd been an upgrade to the Teensy tool, which affected how it built for the device, and so it exceeded the memory capacity, and we have the adjustments. But if nobody in the team directly is actively working with, say, an ESP32, then it's going to take time, unless people are really persistent, because it is such a small core team, and then associated PhDs such as myself. So yeah, just letting us know, being vocal about it when things don't work would really help, and submitting also, if you have the time to make a fix, submit a PR.
Opening an issue is the first thing. If you have a working PR, it's very much better, obviously. Yes, at least we have a trace. If you open an issue, we have, you can come on the Discord channel. Speaking with people that are, some of them working on Teensy, SP32, and yes, this is the idea of having this Discord channel, and then hoping we can have fix, be part of the official release, and so on, like any open source project, obviously. Maybe we should move on to next, because Jan, you are supposed to demonstrate a very new feature. One more thing.
Is it working? Can you hear me? Yes, okay, I can hear me myself. Okay, so I'm going to present a new functionality, which is, at least we were expecting it for many years. And this is more generally a kind of not turning point, but important direction for the Faust language. Let me explain the idea. And I think that the talk of Tommy gives you a kind of idea of that. When you program in Faust, basically you have all these primitive functions like plus, multiplication, delay, etc. And then you have ways to compose these elementary circuits into more complex ones. So basically, you were only doing composition of primitive objects. So the only way to create a new circuit was to compose to other existing circuits. What you can do, especially using the pattern matching that Tommy demonstrates, is the fact that you can create functions from existing circuits, for example, for doing auto differentiation. So this user level function is of a different kind. It's a function that takes an existing audio and transform it into another one. So currently, the only way to do that is by using this pattern matching. There are no primitives in the Faust language that transform existing circuits to create a new one. So the new direction, a new opportunity for Faust is to introduce this kind of primitive functions. So it's not going to be new primitives on the audio signal itself, but new primitive in the way you create audio circuits, not only by using the 5 composition operation of the block diagram algebra. Is it clear what I'm saying? Okay, so it's a round table, so feel free to ask questions, etc. So I'm going to show you 2 of these kind of operations. So operations that transform existing circuits. The first one is on demand. And here it's written on demand and co, because we will see that currently we have just on demand, which is implemented, but there are many other functions that we want to implement, and I will present them. Another one that I will present in more details tomorrow is widget modulation. But for the demo, I will also use already widget modulation. So you will have, I will speak of widget modulation today, but also tomorrow in more details. Okay, this is the plan. This morning I tried my demo and everything was crashing. So I don't know in what state. So how do you say that? Not too, pas trop sévère or whatever. Not too harsh about my demo. But it was not only my fault, because this morning there was an update of Chrome. So I don't know. So sometimes they break. This is the problem of doing everything in the web. Sometimes they break things and it doesn't work well. Okay, so now I'm going to present on demand and explain the idea. And this is not a new idea, because from many years we were in need of a way to do multi-rate computations in Faust. For example, you can write an FFT in Faust. There is a super nice implementation by Julius Smith. It's completely recursive. It's super nice to look at the diagram, etc. It's very explicit. And Julius, which is an expert in DSP, said it's the most beautiful implementation of the, okay, he wrote it, but also he said it's the most beautiful implementation of the FFT ever saw. So it's super nice, but the problem is that you can't use it, because then you are going to have an FFT every sample, which is not what you want. So there is a need of doing multi-rate, for doing spectral computation, for doing oversampling, or sometimes to do undersampling. So these were the motivation that in a previous project, we tried to implement this kind of idea of multi-rate, and I'm not going to detail all this, but using two primitives, vectorize and serialize. And so this was in 2019. We wrote a nice paper with all the proofs and all the type system, etc., but we never implemented it really because it was too complicated. So, and you know, when you design things, if things start to be too complicated, it's that the design is wrong. And why it was wrong? Because we try to implement this multi-rate stuff at the signal level as operation on signals. And this is not what Faust is doing. Faust is a language to describe not signals, but circuits. So it must be a primitive on circuit. So another attempt that failed also was to use this enable and control primitive. This one is a secret primitive that is already in the Faust, but we never really give publicity about it because we thought it was wrong. So, but it's here. You can use it if you want, but we advise you not to use it. And the idea was nice, and I still believe it was quite elegant in some way, was the following. Let's say that you want to mute out some effect, for example. So basically what you do when you are using a mixer, you just shut down the levels, so to speak. So the idea was that enable was a kind of multiplication. You have some generator producing sound, and then you have a slider to control the level of this sound. And the idea was when you reach 0, then you stop computing the producer of the sound. Well, it sounds reasonable to do like this. But the semantics of that is horrible. Well, it's not at all the semantics that we want for Faust. And as you said this morning, semantics is super important. And it's super important in Faust also because having a clean semantics, we know what a program is doing, and then it means we can make many transformations of the program by just knowing that what it's doing and making sure that the transformed version is still doing what it should do. So it's super important to that. And it's also super important because in Faust, I don't know who is familiar with that, but there is the automatic mathematical documentation system. The fact that you can take any Faust program and you can export, even create a PDF automatically that describe the semantics of your Faust program, but without using Faust. The idea is that the programming language is not a good way to preserve musical pieces, so to speak. It's better to have a mathematical description of that, because mathematics evolved very slowly, and we are pretty sure that we will understand the mathematics notation of today maybe in 2 or 3 centuries. Faust is not that sure, probably. So, so this is why semantics is super important, and this is why sometimes in the community people say, why don't you do that, etc., because it doesn't fit with the semantics. It's not that we don't want, but this is something we will never break. It's super important to keep the semantic very, very clean. So, so mute, enable, and control were something that is still available, but we don't, will not maintain probably. And, oh, why is that? Why I don't see all my screen? Okay. Okay, so, and now we come to on-demand, which is and I think on-demand is the right way to do things. So, in 2020, I don't know if Till Bowerman is online, but if it's online, I say him hello, because he asked on the mailing list, okay, how can we do demand rate computations in Faust? And it was not really possible. Demand rate computation a la Supercollider. So it was not really possible, but we start thinking about how we could do that in Faust. And so we provided the specification in a month after. In 2022 at IFC 22, we presented a kind of prototype, but it was just generating pseudocode. And today we're happy to show you real code using this on-demand. Now I'm going to explain what this on-demand do. But basically it's super simple. The idea was to have a single primitive where we can do at the same time multi-rate computation, but also call by need computation. The fact that you say, okay, we have a circuit, but you don't want to compute it at any rate. You want to ask for the next computation by controlling that with a clock signal, so to speak, like you have in electronic circuits. And that's super interesting because we can do multi-rate computation, frequency domain computation, upsampling, downsampling, but also this call by need computation, and basically where you pay for what you use. And this is important in industrial application of Faust, where people do a very large synthesizer under user control, where the user can choose to connect, to use, or some module, etc. In the previous model, everything was running always. And so obviously, if you are running on a laptop, it's the CPU goes super high, you use all the battery, and that's not what they want. They want to show that their VST plugin, for example, doesn't consume any CPU if you do nothing. And this is why what we can do with on-demand. But it's not the only application. And there is something, and this is what I want to show you briefly. There is something super nice with that, is that you can use all the DSP approach to go into a more composition way to think. So because one step is not a sample anymore. It can be a clock. It can be you can run a Faust code step by step, for example, with this on demand. So it's super powerful, and I hope that we will have libraries of. It will never be a language for music composition, Faust, but we have the opportunity to go into that direction. And I think that's going to be super interesting for many people. Okay, so what does it, what is the intuition between this call by need? So you have this kind of patch, so you have the multiplication that takes two input signal, and then you take the absolute value of this multiplication. The idea of the call by need or on demand is that you go in the reverse direction. You ask to abs value, give me the next value. Abs value say, okay, I need to ask to the multiplication, give me the next value. The multiplication say, okay, I'm using the input signal, just take two value of the input signal, the current value, and then compute the result. Give the result to apps, and apps give you the result. So you have a demand that go in one direction from the output to the inputs, then the result that go back from the inputs to the output. In Supercollider, they have a special unit generator for that. So it's two separate worlds. The idea here is that you take any Faust program and you turn it into an on-demand version of it. Okay, so how does that work? Well, it's quite simple. the observation, again, as I said, the simple semantic is super important, so we want to keep it. The observation is that going from the output to the input, the result of that is that at some point you reach incoming input signals and you sample them. So basically, this way going from the output to the input and back to the output is just going from the input to the output, but not on the regular inputs, but on sampled version of the input. And by doing that, you keep the simple semantic of Faust. So, and this is explained in this semantic rule here, which probably it's a little bit scary, but it's just say that. It says that on demand of any circuit is this circuit applied to sampled version of the input signals and by maintaining the result until the next demand. That's all what it says. But it has a simple and well-defined semantics. Okay, so we can skip all these details. And here is an example. We saw that when you want to do granular synthesis, for example, you use a lot of sample and hold. Here is the way you write a sample and hold in Faust, normal Faust. And see how elegant is it sample and hold with the on-demand. It's philosophically quite nice. Sample and hold is the identity functions in a on-demand. That's it. So let's look at the generated code. So when you use on-demand now, it will introduce some if code in the generated code so that it tests if it has to run this part of the circuit, and the code is inserted inside the if. So here we sample the input. We see if we want to compute the identity function. If we want to compute it, we store the result into this perm var here. And then the output is just a copy of this perm var. So the last value that was sampled is outputted. Is it clear so far? Okay. Okay, so this is the way the sample and hold old-fashioned works, and here on the noise. But you see here, you have a noise generator. So you want to produce a value every beat, for example. So you know that the noise generator is always running, and you capture a value and you maintain that value. You sample and hold for that. But it's a waste of computation, so to speak, because all the other values are lost and you do computation for nothing. And here the way it works with on-demand. So you see that the noise generator here is encapsulated into an on-demand. And the bit here is used to control when this circuit is going to run. And so it means that in this case, you will have as output all the values of the noise generator, one after the other. So here the code of this sampled all the noise, all the fashion, and this one is the new fashion. So you see here that you have this the beat generator here, the second line, and then if the beat is 0, so if you waited the amount of time, then you do the computation. So you first have this random pseudo-random number generator, then you transform that into a noise between -1 and +1, and you store the result. And that's it. So the computation is not only more efficient, but conceptually it's super interesting because you run the code. This DSP code is no more DSP code. It's, you control when the computations are done. Okay, so this on demand will have several variants that I will briefly present. Yes? Yes, produce the next. Exactly. Exactly. So it's different from the sample and old-fashioned way. Exactly. So it's, you can imagine that instead of you take all the samples produced by the noise generator and then you realign them on the clock bits. So, and one sample is just reproduced for all the duration of the bit until the next one, etc. So there are several variants that we are going to implement. So first of all, oversampling. It's going to be a very crude implementation, no filters. You will have to do all this work by yourself, but it will run n times faster than the clock of the surrounding. We need to have a specific primitive for that because it's important that inside the oversampled circuit, the vision that you have of the sampling rate is corrected by this factor, so that all the libraries of filters that you have and the conversion between 1 second and the number of samples should be correct. Then you can apply all the filters. And we will have the same undersampling. So again, it's going to be an integer value. Say, okay, do that computation once every 16 samples, for example. And again, this is like the current on demand, but it will have the vision of the sampling rate adapted to this factor. So on demand, oversampling, undersampling. We will introduce the idea of having a switch to have many different circuits that should share the same number of inputs and outputs. Each circuit should have the same number of inputs and the same number of outputs. But then using a control, you can easily switch between one behavior to another. For example, you can, if you have, I don't know, a reverb and you want to deactivate the reverb, you want to switch between a reverb behavior and a strict bus behavior, so to speak. Yes?
So for the oversampling, why couldn't you do it directly with on-demand?
Because
like, instead of having a clock saying like 1 0 1 0 or
sure.
whatever, you could say like 2 3 4.
Exactly. The reason why, okay, so it's absolutely right. You can imagine to have a more complex clock signal that gives the number of iterations. 0 means that you don't want to compute, and 8 you want to compute 8 times. The problem with that is that I don't see how we could have a coherent vision of the sampling rate inside the circuit, because it's going to always change. So this is why we have separate primitives. It again is the same on-demand technology. The only difference is that in this case, it's stable, and you know how to compute the sampling rate vision inside the oversample. Yes.
So you also have the oversampling parameter as a compilation.
Yes, it should be constant. Yes, yes. Okay. Okay. In this vision, you the multi-rate is, you cannot do a compress MP3 compression, for example, because you see that the input rate is always the same as the output rate in this approach. But so it's not completely general, but I think that it will solve many problems. So the switch it's going to be super interesting also. And we will also introduce an interleave operation. Yes?
Sorry. So then for the under sampling, so there's going to be a difference in the generated code between under sampling and doing on-demand.
Probably not. The only difference will be on the vision of the sampling rate.
Okay.
That's all.
Because for upsampling, then of course the code is going to be different. Like, because then you need to add like an extra for loop or something like this somewhere. Yeah. But in that case,
yes, just modulo equals 0, something like that. Yes.
Okay.
Sure. So interleave is going to be, let's say that you have an FFT, and you will use interleave of this FFT so that it appears as just one input signal and one output signal. And you remember that I show you briefly this vectorized and serialized approach that we had. So basically, this is what interleave will introduce. We will wait, let's say that we have an FFT with 64 inputs and outputs. You will wait to have 64 samples. Then you will distribute this 64 sample to each of the inputs of the FFT, run the FFT, collect the 64 FFT, spectral transformation, inverse FFT, etc. All the, and then you will collect the outputs and then interleave the outputs for the output. So okay, so we think that this should solve most of the problem that we have currently. Okay, so I'm super excited with this composition style type of, and this is what I'm going to try to demonstrate. You remember the demo that crashed this morning, so I'm going to try it again. What's interesting is that the generated code is super efficient. We still have the simple semantics, and we are going to be able to preserve things. And also it's in the Faust style. We spoke about idiomatic Faust, and these primitive on circuits are more idiomatics than primitive on signals, so to speak. Is it clear? Yeah? Okay, so demo. No, okay. Now, before the demo, j'ai encore du temps? Non? Ah oui, d'accord. Ah, yes, thank you. Okay, so I will present two examples that use on demand. The first one is Euclidean rhythm generator. Who is familiar with Euclidean rhythm generator? Okay, everybody, more or less. Okay, and so it's possible to have an implementation in Faust, normal Faust, but it's super elegant with the on-demand. So basically, how things are done. Let's say, so you have a number of pulses that you want to répartir. How do you say répartir? To spread out on a number of steps. So basically, P is the number of steps. So basically, you increment the counter, and you take it modulo the number of steps. For each step, you multiply it by the number of bits that you want to spread out in this number of steps, and you take the modulo by the number of steps. And then you check if the number that you obtain is less than the previous one. If it's less than the previous one, this is a place where you need to put the bit. And that's all what you have to do. And the fact to do that in on demand, using the delays, the recursion, etc., of Faust, it's super simple. At least I find it super simple, but not sure. But okay, so and here, how do you use that? So you have a clock that comes, you multiply by the value delivered by this on demand stuff that will say you 0 when there is no bit and 1 when there is 1 bit. But also you drive this by the upfront of the clock. So each time there is a clock, you run it once, and then the output is the clock multiplied by the result of running at each clock. And that's it. Super elegant. I love it. Okay, and so this is a different way. It's more compositional, and this is what we many years ago we did with CLC, which was a list-based composition environment. The idea is the following: is that you create a loop, and in this loop you put values, but so the loop has a size, for example, I don't know, 7 positions, and maybe every 11 steps, you replace one of the value in the loop. So it creates a kind of permanence and variation about the loop. And this is how you can write that in Faust using the on-demand, which is, where is the on-demand? Okay, here it is. Okay, so basically you have, and here the idea is to generate random nodes. So you choose a value, random value between 2 MIDI keys, and you feed that into the loop with this system that changes the value from times to times, and then the output value is converted back to frequencies. Okay, and that's it. And so this is what I'm, the demonstration that failed this morning, this is what I'm going to try again. Okay, so let's start first with this. I'm just going to start first with the clock. So it's going to. Okay, so it's a little bit. Okay, so it's a clock. You can stop and run the clock. Okay, so now I'm going to put here and how it's called again? Forgot the name of the function that I want to use. Euclidean, I guess. Yes, Euclidean. Okay, so I want to. By the way, this is a special version of the Faust IDE that, thanks to Stefan, has the on-demand in the. So currently the state is that we have in the old CPP backend the on-demand, and in the special version of the WebAssembly backend. So you can try it. If you go to orlare.github.io/Faust IDE, you can use it. Okay, so what I want now to do is to put here Euclidean of 0. Okay, so here I have the clock, and here I have the Euclidean. So let's do first something. I have 4 steps and 1 pulse. Okay, now I'm going to put 2 pulses. Okay, 2 pulses is not very interesting because it's equally distant, but 3 pulses. Okay, when you are bored listening to clocks, you tell me, okay. But I can stop it. Okay. Okay, so this is Euclidean using, okay. Now I'm going to use this, I'm going to use these, let's do something else. I'm using this VCO module. Okay, so okay, I can change the frequency. I can change the wave. Okay, oh, VCO. If you look at the diagram here, you have this VCO. So you see that VCO has no input. The only thing that you can control is using the sliders. But it would be nice if, let's say, you want to do frequency modulation. How can you do that? And this is where widget modulation is interesting, because it's going to create on the fly inputs in your new additional inputs in your circuit without having the implementer of the circuits doing that, thinking of that. I'm not sure I'm clear, but okay. So let's say that now I want to. Okay, let's stop that. I'm going to use this key generator here. But now I need, so this key generator will generate some frequency information randomly. And now I need to say, okay, I want to turn the frequency knob using this value, so to speak. So here, how I do that, I use this bracket notation here. And here I say what I want to change. I remember that looking at the user interface, there was something called frec. Okay, so I write frec here, and then I tell how I want to combine this the value provided by the knob with this additional voltage control, so to speak, input. And I say that I want to add them. So I put a plus here, and then I put an arrow to say, okay, this is what I want to do. Yeah, don't look at that. We need to find a better way to represent things. Okay, so now I have this. Okay, I can control the frequency here. Okay. But now I can use this key generator. So let's put it in a length of 1 and a renew of 2. Okay. And put the delta here. Okay. Now every time I'm going to press on trig, it will generate a new value. It will put this value into this loop system. Okay, not super interesting, but if I increase maybe the delta. Okay, let's, instead of pushing the button by hand, use the clock generator to control this. Okay, so I see that the button is called trig. So I can again use this system here to do that. So here I'm going to put brackets here. And now I'm going to say that I want to control the trig value. And I'm going to use, so the circuitry that you use to modulate, you can can be any Faust circuit that either has two inputs, for example, one for the slider, the value of the slider, and the one from the additional input, and you explain how you want to combine them. So mod is a way to combine the value provided by the slider using an audio signal. So this audio signal is between -1 and +1. The idea is that you take the current value of the slider, and this is for 0. If the signal is 0, you don't change the value. But if the signal go up to 1, you go from the current value to the maximum value. And if the signal is -1, you go to the minimum value. And you can do that because in Faust, you can know what is the maximum value of a signal and what is the minimum value of the signal. There is a kind of introspection in the Faust language that helps you doing that. So just by having these two inputs, the slider and the modulation signal, you can, even from that, know the current value of the slider, but also know its minimum and maximum value. So trig mod. And now I need to put here the clock. Clock and do the connection. Okay, so now we have the clock. We don't have to press this button. Okay. I can run. Okay, not super interesting, but if okay. Okay, maybe I should leave some time for the question. So, okay, it's a third of the demo that crashed this morning, but again, it didn't crash. So I think I will stop here, and tomorrow I will show you in more details how this widget modulation works. But we have time for some questions. Thank you. So I am, yes, there's a question.
Are these primitives going to be available on the Box API?
Yes. Yes, sure. Yes, yes. Yeah, I understand your question, obviously. No, sure. Okay, sure.
I think when Jan is now, I have something to say. Since 2 years, Jan is now concentrating again on the French language, and he moves so fast that he lost almost everybody in the community, because you in some way you demonstrate the new on-demand and the widget modulation, and I think it's probably difficult for you because there are two new primitive into the language. The widget modulation is something per itself, which has to be explained a bit longer tomorrow, and the on-demand feature, it's also something very powerful, interesting. So now the demo was probably a bit difficult for you to follow because of this reason. I think
this is what Stefan says. He's right.
It's because you don't know Faust, Stefan.
It's okay. I mean, for me, I imagine you guys know nothing about this new thing, and you have a
No,
lot of
probably,
it's
yeah,
probably
sure.
difficult to follow. But so, yeah.
Especially there is no paper right now, so.
And yes, on the more engineering things, so we have this new on-demand feature running into the Faust IDE, but we still have a lot of work to make it work on all backends, which is part of my work because Jan is working on an old backend, old CPP backend, which is simpler to make evolve. And so we have to do that. And in this new development, there is also new ways of generating delay lines. There are a new scheduling system into the compiler. So there are a lot of new things into the compiler that we have to check carefully to be sure we don't break anything. To be sure we gain even some CPU, we can gain some CPU speed with the new delay line implementation, but we have to check everything. So it will take some months to have everything on the official Faust release.
Pierre, derrière, il veut poser une question.
So thank you a lot, first of all, for this awesome primitive. It gives many ideas. A question about the syntax. So it takes as an input like a clock signals.
Yes.
And
no. For the widget modulation.
No, for the on-demand.
Yes.
For the on-demand.
Yes, it takes a signal. Well, it can take any signal, but it will use 0 to say, okay, I don't compute, and anything not 0 to say
Anything
I will
not
compute.
0, okay.
Yes.
And so it's on-demand, open bracket, and
Exactly.
your process.
Yes, exactly.
And an extra input for the clock. Okay.
Yes. And if you go on the Faust IDE, the one I'm using here,
I'm on it.
You can write process equal on demand, open parenthesis, underscore, and close parenthesis. And you will, if you look at the diagram, you will see that your cable will be inside an on-demand circuit, so to speak.
And what's the clock for this particular process, for instance?
What
is the clock rate of on-demand underscore?
The clock rate on demand underscore, it's going to be what you put.
There's an input. I see
it
here.
requires two inputs. The one,
I see it. Okay.
It's like a sample and hold.
Semantically,
it's like a sample and hold.
Okay, perfect. And second question, like, we will have the FFT soon. With that, like someone will write like Julius maybe with on demand?
No, we have already the FFT, so we wait to have this interleave stuff, which would be more convenient. Currently, you can use on demand, but it means that you take an input signal, then you let's say that the FFT is 32. You take the signal delay by 31 and go to the first input. Then the delay 30, the second, etc. until the end. And you put that on an on-demand, which is the +1 modulo 32, basically.
Okay. And then
equals 0. And that will do the trick of running the FFT with the appropriate information once. But you see, it's a little bit heavy because you have this delay line, you have 32 access to a delay line, etc. So we can do, the interleave will be more optimized. Conceptually, you can already do that, but interleave will be more optimized for that.
Okay, thank you.
Yeah, there's a question.
A really exciting presentation, and that was exciting for me because I was also wondering how do I integrate my DSP language into the kind of control rate processing world. So then I got one question, and for in the on-demand world, is there any way to obtain the time period since the last computation is done in any way? Because
yes, if you just write +1 tilde underscore, you create a counter, and this counter will give you the time since it's. So this is something I did not mention, but one of, not the difficulty, but something we had to take care is that a circuit in a different on-demand value. So if you have a +1 tilde underscore, which is a counter, if you put that counter into an on-demand or outside an on-demand, it's going to be a two different counter. So it will count effectively the time into this on-demand.
In terms of the performance, so if we write the FFT code with on-demand primitives, so in the compiled code, the CPU every sample check if the computation should be done, do or not.
Yes, you have a condition
and is it possible to optimize the conditional check?
It's probably possible if you run in, we have several compilation strategies. There is a scalar mode, which is just one giant loop, and there is the vector mode. And the vector mode is by vectors, so to speak. So you can imagine that in this case, you check just once if the condition only depends on sliders, buttons, etc. So maybe in this case, you don't have to check every sample, but every block of samples.
Okay.
Yeah,
Thank you.
But it's not done yet, but it's probably an optimization. But yeah. Okay. Yes. It's not working.
Is it already possible to use it somehow, or?
Yes, in the Faust ID and there is some branches, but are not public that use it. But if you really insist, it's possible. Yes.
Okay, I really insist, maybe.
Okay, but it's going to be a branch where you will have to use the old CPP backend, as Stefan mentioned, where the vector modes and parallel modes will not work with some limitation. But at least for CPP, for C++, you will be able to use on demand. Okay, let me know and I can open an access, or we will think of something with Stefan to make it available.
Thank you.
But it's not once you give something, then people will start complaining that it's not working exactly like, and or people will start to build things, and then they will complain that okay, now it's not supported anymore or whatever. So it will at your own risk and perils, so to speak. Okay. Yes, Tommy.
Just as an observation and to tie back into the earlier discussion, perhaps when this gets a hard launch, it would be a good test case for blog post, video, call out to the community. Anybody has some interesting ideas for applications of the new primitive? see what suggestions come via the Discord and include those as like, here's a useful and interesting example of how to use it. That's, I don't know, could spur some ideas.
Convolution would be nice.
Yes. I was sure you were going to say that. I don't know why, but I was sure.
Well, that's a hard one.
Sure. Okay. So.
Aperitif.
Aperitif. Okay, thank you.
Posso staccarlo?